All right. Hello, welcome back. Um, I want to continue a little bit more because I really want the player. Okay, maybe I should explain what we're doing here. So basically, we're learning a little bit about BSP, binary space partitioning, and how to use it for things like render optimization and also collision detection. So, uh, so right now, what I'm trying to work on is the player collision detection. What we have right now is we have this little world that we can move around in, and we do have some sort of collision with the player, but it's like a little bit buggy. Sometimes you go into the wall. It's like the player is like a point and not a, the player doesn't have any kind of volume or anything like that. Yeah, you can slip through like some of the points in the wall, and but yeah, it works. It kind of works. It just there's some amount of bugs, and also we have this intersection point calculation that we can use to see if you shoot a gun or whatever, we can see where it should land here. So we got that, but what's kind of missing is like having a volume. So it's easy right now to what we can do is we can cast a ray, like a line out, and see where that lands on these walls. But what we don't have is like a volume to like keep that volume, having collision for the volume basically. And then I want to plan to do is I want to try to like improve the graphics a little bit, and maybe add some monsters that you can shoot or something like that. So that was actually and then we have this little kind of demo using like old school techniques. Hey, Chaz, welcome. How do you approach learning new things like coding and writing? I'm just banging my head against it until it enters my brain. No, but what you need is basically, I guess, you use maybe a little bit of creativity, like you have some sort of idea that's what you want to do, and then a way to kind of expand on that idea. I have some sort of basic knowledge, about vectors and stuff, so and collision detection and stuff like that. So when I heard about BSP and it was related to other like topics that I've explored before, then I had like a kind of basic idea of what it was. But you don't really need that to get started though. But I mean, learning vector maths is probably a very good idea if you want to use something like game dev. But yeah, as I've done before, like if I'm facing a problem that I can't solve at the time, usually if I go away for a while, like I've been you can either power through, but that requires so much energy and probably not worth it because it takes longer. Like if you're tired, if it's at the end of the day, you feel tired, there's no use in actually tackling huge problems like that, especially if you've gotten stuck, unless you feel like you're on the cusp of something. But it often helps to move away from the computer, do something else, move away from the problem, your brain will sometimes subconsciously continue working on the problem. Maybe you'll sleep on it, maybe the next day, maybe you'll dream of something, a solution, maybe next day, you're making coffee or tea or whatever, and suddenly the solution appears in your brain. Now this hasn't happened for me for this specific problem since yesterday, but I have slept, I have refreshed, and new day. I've eaten breakfast and going in with a relative clear mind. So you start again with new energy, and you go in and maybe you think of another way to kind of tackle the issue. And that's what I did. So right now I asked AI here to show me a mathematical formula for calculating the swept volumes intersection point with a line. And I didn't do that yesterday because I tried to kind of brute force my way to a solution. But, and that's the thing. You have to have patience. That's what I was getting at. Patience to actually go ahead and persist to solve a problem, persist to learn. Because in the end, when you actually get it working, you have actually moved forward. You have actually learned something. Like right now, when I started with learning BSP, I didn't even know what it was. And I didn't even know that it was a binary space partitioning. I heard the name, but I didn't really think about what the meaning was behind the name. Now I have an intuition about what it is, how it's useful, how you can use it, and I can understand how you can apply different approaches to it to solve different problems. And yeah, now it's of course BSP is not a modern technique, so some could say that it was a waste of time, but I don't think so, because learning BSP is not only about learning BSP, it's also about learning spatial partitioning algorithms and vector maths and all that. So you get more used to that stuff, and you can probably learn other similar things more easily in the future. And I love learning new stuff. I've always been, I have I've always loved to learn more things, when it comes to programming languages and maths as well. More so programming languages, I would say. I'm more interested in programming than maths, but it helps if you're interested in the subject, of course. So I'm not really, for example, I'm not really a designer. I was kind of adjacent to that maybe all my life. I have, in my family, there's a lot of, artistry or whatever. But I personally, I'm more on the logical side. But, so I don't go after the things that I'm not interested in. I go after things that I'm interested in, such as programming and algorithm, game development, yeah, I don't know. It's like a combination. You have to have patience. But it's also different. If you're in school, you have a deadline, which I don't right now. I don't really have a deadline with this stuff. I can learn at my own pace. I don't have to think about, well, it's not entirely true, because I don't have all the time in the day and all the stuff. So I do have some kind of time but I don't have a date that I am saying well, I kind of decide myself what the date would be. For example, I don't want to spend too many more streams on this project. So I can just start. But if you're in school, you have a deadline, and then you have to have a more structured way of learning. So I don't really structure my learning like that. Like, for example, yeah, you have to read these chapters. Okay, well, just divide the chapters up. Just think about, okay, what's the deadline? Okay, when is it feasible for me to have learned this? No, sorry. When do I need to have completed this? Take those days, divide up the pages on those days. Okay, I have to read 10 pages a day. Okay, let's do that. 10 pages a day. I don't know. Yeah. I don't really have a super good, maybe, way to learn things. I just go ahead and do it. I don't know. Yeah, I don't know. That is such a bad answer there, but yeah. I don't really. That's it. I don't really have a good way. I just try to do it. I try to explain how my process is, but the truth is, like, I don't really have like a process or whatever. I just, a question pops in my head, I Google it. Now we have AI, we can make use of it a little bit. I don't want to use it too much to feel like I'm cheating or whatever. There's a point in actually trying to think for yourself and try to figure out an answer for yourself, because then you learn more stuff than just that answer. You learn how to get to the answer, and that is very important, because then you can get to other answers as well. You can use it to learn other things that maybe the AI doesn't know, for example. But yeah. So I hope that give you an answer to the question. I don't know, you probably ran away a long time ago. Okay, so anyway, we were doing this volume algorithm here. So I am going to continue with that. So what I did was that we had some trouble thinking about, okay, well, if we have a volume and we have the BSP, we have several lines that we can collide potentially with. How can we have a volume that is correctly placed and correctly calculated the velocity of the volume? And the AI was talking about the Quake algorithm. Well, I kind of asked it, okay, well, how does Quake do it? And Quake does it with a hull that creates a new BSP tree, and then it has a actually, yeah, so that is the thing, like, it uses another BSP tree, which I don't know how to calculate, so I'm trying to skip that part. But they calculate a new BSP tree depending on the hull size, and they extrude the level. So it's essentially, what you get is the BSP tree, but it's like adjusted to fit, to work with a specific hull size, player hull size. And then you just cast a ray as normal, and if you get an intersection, then you know that you've collided with the hull has collided with the original BSP tree. And yeah, this algorithm looks exactly the same as before, except we have an overbounce, which is like we're correcting a little bit. I should actually try that, because that might solve the issue with the facing, that we're wall facing, like we're going into a wall. So what we'll do, not in collision, but we'll say, yeah, here we try to calculate the intersection point. So what we're trying to do is we're creating a new velocity. We have the position here. What we also want to do is move the player away from the wall a little bit as well. So we have the intersection point, and then we calculate a small this is like the over bounce, and we kind of adjust the position here. However, then down here we're like ignoring this. So what I'm thinking is that instead of doing this here, what we'll do is we will we just want to subtract the overbounce. Let's actually rename this to overbounce so that we see that it's kind of the same thing. And maybe this will solve the kind of wall facing issue. You can see we're kind of bouncing away from the wall a little bit. And it might have solved it. Because before, it's like when you got to the midpoint, we actually faced through the wall. It seems to have solved the issue. Okay. Because of it's probably because of some like floating point error or something. Why do you use NeoVim? Because it's my favorite editor. And I can configure things as I please. And I can make plugins pretty easily if I want. And there's a lot of plugins to choose from. And also it has Vim bindings, which is really nice. What editor or ID are you using? Fat Orange Cat. Okay, so that solved that. We probably don't need this to be that large though, so let's decrease it a little bit so that we don't get like this weird bounce effect too much. Yeah, that seemed to have solved the wall facing issue. So I mean, okay, this is actually, you know, this could be like good enough to be honest. But actually, wait, what's happening here? Is that a face issue or are we just past the wall at this point? I think we're just past the wall. You use you use VS Code. You try to use NeoVim, but I have skill issues. Quite a pain. I mean, yeah. So, yeah. The thing is, like, to learn NeoVim as a text editor, it's very simple. Like, you only need to learn like 4 different things. You need to learn how to open the editor. That's very easy. How to open a file, and then how to save the file, how to quit. Okay, maybe there's more than 4. And then also just how to enter like writing mode and exiting writing mode. So that is, when you've done that, you can basically just use NeoVim as a text editor. But to use it as kind of like an IDE, you know, you need a little bit more. You need the plugins. You probably need, I mean, I'm using a plugin manager called LazyVim, or whatever it's called, which is really nice, and you can configure. You basically put a bunch of dependencies as you know, GitHub. Well, not really URLs, but it's like names. It's like the author / repo. And it also depends a lot on what language you want to use. Like what language are you trying to work with? But yeah, for Zig, it works pretty well, I would say. It has, it has the LSP support, so it works with the same LSPs as VS Code has. So that's really nice. The one thing that can be kind of weird to set up is I would say the debugging, because it depends on the language. But for Zig, for example, I tried to set up the debugging stuff for Zig, but I think I couldn't get it to work, and the VS Code had like a better guide or better like integration there, so I ended up just using like VS Code for debugging if I actually needed to do that. I've actually not debugged Zig like running the debugger, and even then it's like where you're using something like LLDB or something like that. I'm pretty sure. I'm not sure now that they changed the backend if you need to use something else, or if they are gonna do their own. I don't know. But yeah, the debugging in NeoVim can be tricky. I mean, it depends. Again, it depends on the language. It's like there's a plugin called DAP, I think, that is pretty nice, but it's only nice if you have compatible plugins for the languages and stuff. And also for me, it's even more bad because I'm using NeoVim in WSL, which is a Linux virtual machine on Windows. So my host OS is Windows and I'm running WSL. And then there's some issues with like debugging because of the file names as well as other stuff as well. So it doesn't get easier. Like it would probably be easier if I was running like Linux natively or like in as a host. But yeah. So some compatibility issues can arise. But I mean, VS Code, if you want to get started with like VS Code, or I mean like Vim bindings, there are Vim bindings for VS Code, so you can like practice on that. Like when I use VS Code, I always, like when I use any other editor, I have to install some kind of Vim bindings, and there usually is Vim bindings on all other editors basically. So just install that extension and you can start to kind of get used to how the Vim bindings work. Well, I very rarely debug, I would say. It's like sometimes it is useful, but most of the time I'm just logging things out in Zig. If I'm doing something else, I'm probably doing web development, and in that case the debugger is actually not in the IDE at all. It's more in the browser debugger. So there I'm just using the browser to debug. Oh, you're using Vim emulator. Okay. Yeah. So that works as well. But yeah, if you disregard debugging, I think NeoVim is pretty nice actually. But yeah, I mean, you can. It's not like it's impossible to get debugging working in NeoVim. It's just that sometimes it can be a hassle, and again, depending on the language that you wanna debug as well. So it's like I couldn't get the debugger to work with Zig, but that could be because I'm running on WSL. Like, I'm not sure. It was a long time ago when I tried to fix it, but then I could just use VS Code. But then it's also like, does the project live on my Linux drive, or can VS Code access that? Like, there's a whole bunch of issues with the whole two systems working together. But yeah. All right, so what are we doing? So the overbounce solved the face walls thing. So right now, it would be nice if we could. So what I tried to ask the AI was basically, okay, well, you were saying that there was like an algorithm, or Quake did like it got the intersection point of the swept volume, but I think that it's just using the second BSP tree to get the point of impact. But then you don't even get the point of impact. You get the point of impact on that tree. How would you get? Then you need to do some translation calculation to get the point of impact on the other tree, I think. Okay, well, anyway, I just asked it like this. Okay, can you show me a mathematical formula for calculating the swept volume's intersection point with a line? Because that's what we need, I think, if we want to... if we want to calculate the player as a circle and get the intersection point of the circle to the line. I mean, technically we're gonna get, I think, 2. But not a swept circle, though. Calculating the swept volume involves finding exact time t where a moving boundary first touches a static surface. In games like Quake or Doom, it's modeled at the intersection moving point. Play center with an offset surface. The wall moved inward by the player radius. The geometry of the intersection. To find the intersection of a swept sphere with a line, we solve for the time t when the distance of between the center of the sphere and the exact and the line is exactly equal to the sphere's radius r. Oh yeah. Wait. The distance between the center of the sphere and the line. Like the closest point on the line. I guess. The position of the player at time t, where t is between... Wait, t is either 0 or 1? Or it's between 0 and 1. Inclusive. So, position of the player is equal to acceleration plus time times... Or, yeah, velocity. Starting position, velocity vector. A wall is defined by point W on the wall, a unit vector, unit normal vector n pointing away from the wall. Formula for time of impact. Now I'm not sure how much I'm trusting AI with this, because I don't know. Maybe it has been like better with mathematical formulas, but some of the logic stuff with AI has been pretty bad. But I guess we'll look at it and see that, okay, well, this makes sense or it doesn't make sense. The distance from a point to a plane or line in 2D is defined by the dot product. The dot product of what? We want the time t, so the dot product of... we want the time t where the distance from the player to the wall equals the radius r. We have the position minus the wall, so we get a relative... The relative position of the player relative to the wall is what this means. And then we dot product with the normal to get r. Or I mean, yeah, we need that to equal r if we want to find the radius. Right. Yeah, that makes sense. It needs to be positive because that we're on the right side of the wall. Or I mean, we're on the in front of the wall, basically. If this was negative, we're behind the wall. So if you have a double-sided wall, then that would make sense. But we don't really have double-sided walls. I don't think we're gonna have double-sided walls at all. So positive here would make sense. Substituting this acceleration plus velocity times time. Okay, now solve for t. Distribute the dot product. Okay, I don't know the rules about, you know, the algebra rules for vector maths here, so I'm gonna just trust this, I guess. So now we have two dot products. We have, wait, a minus w? Right, because this is just a plus minus w. So we're extracting a minus w, and then we add t. T is extracted as well. T times... I mean, the dot product is simply an algebraic expression now. So you could derive this from that, I guess, if we really wanted to. Because it's kind of simple calculation, actually. But yeah. So we've got this acceleration minus the wall, so, and then t times this. Makes sense, I guess. But velocity is not relative to the wall, so that's kind of weird. Maybe it doesn't need to be. Okay, whatever. Isolate t. Yeah, this gets just moved over and then divided by this. Okay. How to interpret the result. T is between inclusive 0 and 1. Collision occurs during this frame. The player is already behind the wall or moving away from it. Already behind the wall? What? The player is moving toward the wall but won't hit it until a future frame. Okay. Oh, I see. So if we do this equation, if t is below 0, we were already past the wall. We didn't actually collide. I see. So that... yeah, okay. So that could be if we're comparing to a wall that is way behind or something. Hello, Polaris. Have a nice day yourself. Okay, and t is more than one. Players moving toward the wall, but won't hit. Okay, so basically these two we don't need to know about, but we do know if the player is behind or in front of the wall, so that's good. And then this one is like, yeah, now we also have a collision. Denominator is 0, meaning the players moving perfectly parallel to the wall will never hit it. Okay, so we have to check for 0 here as well. Find the intersection point once you have T, the exact point. Yeah, so we just take this is the position. Well, we can figure it out, I think. The actual contact point on the wall. Position when we're hit minus R N. The math allows Quake to be pixel perfect universe, ensuring players never accidentally face the walls. Even at extremely high speeds, would you like to see how this logic changes when the player hits a corner instead of a flat wall? No, because it's just a repeated thing, I think. It's just, we're doing this for the first wall we encounter, and then we update the velocity, and we do this again. I guess you can do it until we don't have a collision anymore. I don't know. The kind of edge case that is going to be different is when you're in a wedge, when you're going into a wedge, or the crevice. Yeah. But let's do this first. I'll just be 1 second here. Be right back. Alright, I got my coffee. Let's continue. So, oh, sorry I missed it. Thank you, ex-sister, for following 35 minutes ago. Okay. Cool. So I think maybe we need like a second collision function. Right now the thing that we have here is for race. Maybe we'll rename this to ray. Cast ray or something. And this would be like, this is like the private function, which is like the one that actually does the work. Let's just do this. Okay, so we need like a similar thing here, which is going to be sweep circle. And it's going to be a little bit different here. It's section info. I mean, really, I think we'll just remove the race because that was only for like debugging. So I think that we'll just do this. This is the node that we are interested in, that we collide with. And yeah, let's just get rid of this ray thing here. And now we actually don't need an allocator or anything when we do that. So here basically we don't actually append a ray, so we actually don't need to do anything there. The only thing we need to do is this one. And there we go. And you don't have init anymore, it's more, you can just simplify it there. Same thing here. And we don't initialize. You don't need allocator, you don't need allocator. Also, we don't have a try now anymore. Oh wait, we do have a try. Actually, we don't have a try because you don't have a try. I wish it would say maybe something if you add an error type. Maybe you don't want, maybe you want an error type, but it would say something like like a warning, or you can enable maybe a warning, like if you have an error like this, an error union return type, but you don't actually return an error anywhere, that it would fix that, or yeah, because yeah, you want to reduce the complexity there. So now we don't need a try there, you don't need an error type. And you don't need to try. And wait. Oh. Right. Now you're not a try. There we go. And I guess I mean, yeah, sure, we can keep this. We don't call this function. Do we want to keep this? No. Let's get rid of this. It was showing the race in a debugging manner, so we could like debug it, but we don't really need to know. I mean, we could make something. I mean, it would be for educational purposes, but I've already shown it, so whatever. Okay, so we've gotten rid of that, so a little bit less complex now. So we have the sweep circle. So basically we have a start and end, and then we need a radius, and we need a root node, and this would be the same, like intersection info, and then we also have the point of intersection returned to us. Okay, now we'll go and look at the equation here that we got again. So basically we need this equation, or we need this formula. So we need to calculate t. So let's calculate the numerator and denominator separately. So we have the numerator is this, so we have radius minus, and then we have a dot product here, which is the acceleration vector minus the wall vector, times, or I mean dot product with a normal. And the wall vector, I'm gonna say this is the center point of the wall, I think. What is this? It was live for it, yeah, creating a game. I'm basically, I'm not really creating a game. I'm more creating like we're more learning about a specific like algorithm that was used in the first Quake game. And I thought that it was also used in like the Doom game as well, but apparently there was another type of algorithm that was used there, a simpler, or yeah, I guess you could call it a simpler algorithm, maybe, I don't know. But yeah, we're learning about it's the BSP algorithm, and they're also learning how to apply it, like how it works, how to create it, and then how to apply it to use it for things like rendering, optimization, and collision detection. So what we've got so far is we have this little demo game here. Oops. Let me just do that to make the compiler happy. So we have this little thing here. Whoops. I shouldn't press space because I was trying. I tried to jump, I guess. So we have this little demo thing here, where you cannot. So you can see these lines and stuff. They are kind of the BSP tree segments that we've done, and they kind of divide the level into their own, like it's dividing the level in rendering spaces basically, and also it can be used for collision detection. So I can not go through this wall here because we are using the beast picture to kind of to calculate that as well. So right now, as you can see, the player can move, like go into the wall, because the player is basically just a point right now. And what we're trying to do is we're trying to figure out how to use the player as a circle instead, so that the player has like a more so that we get stuck like maybe out here instead of straight at the wall like this. So that is what we're trying to do. Okay, I'm gonna try and follow this. So we have this little formula here that we are gonna try to use. Now I'm not certain about this wall vector, what it actually means. A point W, a wall is defined by a point on the wall. So I'm gonna say that this is like a point on the wall. I'm just gonna take the center point of the wall. It feels like there should be like the wall size should matter, like how long the wall is. Like it does have a start and end position. Maybe that changes the equation, but okay, we'll see. So what we're doing here is we're taking these 3D coordinates, we're turning them into 2D coordinates, and then we call the inner function with these new things. And we need a radius, start node, intersection info, depth. Actually, we don't need depth now, I don't think. As well. Why was that even? It's not even used, right? It's just it's just like doing that. Okay, so let's remove that, and you don't even exist. So let's copy this signature. Are you a game dev, Mr. Vibe Checkpoint? Let's see. Starter, whatever. Yeah. So yeah. So this is the same thing, the entry point here, and here's the actual like algorithm down here. So I mean, I guess we have the same thing here. If the node is empty, we return null. If the node is solid, we have, well, I mean, if it's solid, this is where it becomes a little bit more confusing as well. If it's solid, we know that we have actually a collision, but the collision is actually happening on the line and not in the node itself. It's like, yeah, we have a collision, but where is the collision at this point? Should we then take I think this probably would work a little bit differently than the raycast. Because we need to do the sweeping before to see which segment. Maybe we do a sweep. We find out what is the position of colliding with the line. Or do we divide the sweep up in two? Just like the raycast? And then the midpoint would be the point of intersection on this line. And then the next sweeping would start at that point and move towards the end. And if that's a split, then it's the same thing. Then we just return the point that we have. And the node here is the last split. So that's exactly the same in that case. So what we need to do here is we do the same thing. So if we are fully behind, repeat with node back. If we're fully in front, repeat with front. Otherwise, can we easily calculate that though? We have to do we have to do like a circle against line. Calculation to figure out if we are actually, couldn't we could take, because we're dealing with a circle, couldn't we take like the normal of the wall add it to start position, wait, normal, and then we scale it by the radius, because the normal is normalized. So this would have a magnitude, the result here would have a magnitude of the radius. We add it to the start position. I was thinking then we're ending up with like a tangent if we rotate this. So now we're at the circle. We're at the edge of the circle that is closest to the wall, I think. Well, I guess it depends on where, if the circle is in front or behind. Maybe we could see if the point is on the front or behind. Yeah, because we know that the point, we can easily calculate if the point is in front or behind. And once we know that, we can do this to get, there's probably an easier way, but we can do this to calculate, and we flip n depending on if we're in front or back. And now we get a point that is like closest to the wall on the circle. And then we compare that to the distance of this point to the wall. But the wall could be like angle. Like, how do we do this? It feels like there's some basic trigonometry or something. Just I'm like imagining different edge cases in my brain right now. I mean, the easy case is like if the wall is just straight, then all you need to do is like, if the point is over there, the circle goes like this. Like, I would like to see, like, the thing we need to do is like find the nearest point on the wall and see if the distance is just between the start and that point. So if we can is like less than the radius. So if we can find the closest point on the wall, and we have the direction of the wall, so we can just cast a ray from, I mean, we don't need to cast a ray, we just make a line from the start position and then in the direction of the wall, which we should have, and we'll just see, we don't even need the direction, we just create a line, an infinite line, and where that intersects with the other line, that's the closest point, and then we compare that with the radius. So I'm not sure if I even need to show, like, explain this here, but so we have, let's say we have a line. Player is like down. What the hell? Player is down here. Okay. It's supposed to be a circle. Okay, there we go. Now, so we have this line, and here's the starting point. Here's, well, hang on. here's the midpoint of the circle. Well, it's not okay. There we go. And what we need to do is, and then what we also have is we have the normal of the wall, which goes out perpendicular, something like this. So that's the normal. So what we do is we take the normal direction and we just use it to create a line with the same angle as this normal here. And we create an infinite line. Now the circle happens to be like kind of in the middle, so I'll just move it over here. We create a line that has the same angle here. So basically something like this as the normal. And this line would go on forever. Oops. I don't know, something like this. And then we simply find the intersection point of these two lines, which we can easily do, which is over here. And then we just compare the distance of these two lines, which is also very easy to do. Pythagoras, now I know how to do that. And then we just check if this distance, if the distance is less than radius or equal. Wait, if it's less than radius, that means, no wait, less than or equal. If it's less than or equal to radius, that means that we are intersecting with a wall, or we're colliding with a wall. Why did we need to do this? I just forgot. Right, we need to do this because we need to know if we're fully behind or if we're fully in front. So we need to do this for both the start position and the end position. And then also, so okay, so we need like, we need to somehow get distance 1, which is like calculate distance line. Does Rayleigh has something like this? Distance line. I mean, we have check collision lines, but that is like if we have a start and end position. Calculate distance line between. So we have like, but now we have an infinite line. So it's basically we just need. What do we need then? We need like. If you have an equation like, you know, y equals kx plus m or whatever it is, we need like k and m. So k is the angle basically, m is the offset, maybe. Hello Blue, welcome back. How are you doing? Yeah, we need to like calculate the line somehow against well, it's gotta be the node branch segment or splitter vector. No. P0 P1. Yeah. So this is like the second line, is start and end. This line is like infinite, which we need to understand somehow. So now we have distance 1. Actually, this would be like line 1. And then we have distance 2, line 2. So 1 is corresponding to the start position, 2 corresponds to the end position. So now when we have those distances, we can check here if D1 and, well, if D1 is less than, or if D1 is, well, fully behind. Wait, no, this is just a distance. Right, we need if we're behind and in front as well. So then we need to say is on front 1. Which we do have is on front, which takes 2 vectors, 2 points. No. Which one is this? We have the relative position from the start to the position, and then the wall. Okay. So this would be start position, subtract P0, and this would be the vector. No, this is still the same, P0 and position. So it's like, here we need to say like is. So we don't need these two, I guess, down. We need to like is on front 1 and is on front 2. Then we return sweep circle, no, underscore, same positions. Same last split, but the node will be the front, same intersection info. Okay. And then otherwise both need to be false, and then it means that we're both behind. Actually, I'm missing something, I just realized. And I will take the back. We do need these two as well, because we need to know if both of these are more than the radius, because otherwise we have an intersection. So actually we'll move these up here, and if D1 is more than radius and D2 is more than radius, then we do this check. So that means that none of those will actually intersect, but there could be an intersection in between though. I guess we need to do this. I guess, yeah, we need to kind of have this if here as well. So it's like if both are on front and none of them intersects. The extremities are not intersecting. I'm not sure if that's clear what that means, but if we don't have intersections on the extremes, we check if both are in front. Then we couldn't have an intersection in between because both are on the same side. Same thing for the back side here. Which means that we could probably we could make this into an if here. Move these out. Move these in. Whoops. If we don't have an extreme intersection, wait, but then I'm trying to think about the edge cases here. So we could still both be on. No, because then if we have an intersection, we actually always go to the next case. However, we might not get into any of these in here. Yeah. So then at this stage, we want to also check for sweeping intersection. But we also want to check for sweeping intersection here. So that's the thing. But I guess we fold out here. If that's the case. Yeah, so only when we have no extreme intersection, we want to check, okay, are both in front or are both behind? Otherwise, we do a sweeping check. And now we come to the algorithm that we were looking at before. All right. Sorry, my phone was going crazy there. Okay. Position of the player. So where are we? We are down here. Right. We need to calculate this t. So now we need this thing here. So we're gonna do, I'm gonna divide it up into numerator and denominator. So let's start there. So we have t equals numerator over denominator, and also if denominator is less than epsilon then denominator is 0, which means something. So, you know, we can't divide by 0. It means that we're parallel, so we won't ever collide with this node, I guess. But that won't happen because we already checked these cases over here. So I think this is like unreachable, actually. Okay. So what is the denominator, or the denominator? Yeah, or the numerator. Wait, is the numerator is the one at the top, right? Yeah, it is. Okay. Numerator is radius minus this equation. So radius numerator equals to radius. Why is this not like defined? Oh, because it's not added over here. Okay. There we go. Okay, radius minus. And then we have this dot product between the acceleration minus the wall. So we actually need the acceleration as well. So this would be like acceleration subtracted by the wall point. And this is where also it feels like we need to... No, actually, because all the walls are planes at this point. So we don't actually need to know the length of the wall. If we have an intersection across the wall, it automatically means we are intersecting, because all the walls, or not the walls, but all the BSP kind of segments span infinitely. So actually, yeah, we only need, I guess we only need like 1 point along the wall then, I guess. So this would be the node branch, and yeah, we'll just take the midpoint, and then this is dot product to the normal, and that's the numerator. We also need the denominator, which was, I believe it was the velocity dot product, the normal. Let's double check in case the AI is actually spot on here. Yes, so the velocity dot product normal. Okay. Now we need to pass acceleration and velocity, so we actually need this information here. And let's add them here as well. Oh yeah, we need that one as well. Denominator. Okay, so now we have acceleration and velocity. Okay. And once we have t, we can see that. Well, okay, so we had a couple of scenarios. If t is between 0 and 1 inclusive, a collision occurs during this frame. So then we know that we have a collision. So if 0 is less than or equal to t, or, well, sorry, and t is less than or equal to 1, then we have collision of that segment. And then if t is less than 0, we won't have a collision, I guess. So we're behind the wall, which doesn't. No, that could make sense. We're behind the wall, so could this ever happen though? Because we're both points are at one side of the wall. I don't think these could happen. Like, these two cases shouldn't happen because we already checked if both points are like either behind the wall or in front of the wall. So the sweep has to collide with the wall, basically. Right? It has to. Because both points are on the other side of the wall. So we have to have a collision at some point. We just need to know when it happens. So this should be the only case that we have. All other cases should be unreachable. Okay, and what happens then? Then we do a split. The same thing we did with the raycast, but now we're splitting to sweeps instead. So we'll do if sweep circle, start position is the same. So first we check the first half. Well, actually, we need the t. We need like the point, intersection point, is going to be. Well, what did it say? Oh, sorry, you didn't see that. Anyway, find an intersection point. Once you have t, the exact point where the sphere center will be at the moment of the impact is this. The actual contact point of the wall is the hit point minus Rn. Okay, yeah, that makes sense. So R is multiplied by N. N is scaled by R plus the hit. Okay. So let's see. So the intersection center point of the sphere, of the circle, will be. Well, I think we have to calculate like start point. So it was like acceleration plus velocity scaled with t. But then that was that, and then we have to, I mean, we have to offset the start position as well, right? I'm pretty sure. So it should be this, right? And then the intersection point is intersection center. And then we can see here that it's the center is, or the intersection point is the center of this of the player minus radius scale with the normal of the wall. So subtract the normal scaled with the radius. Yeah. We'll see if this works. Okay, so once we have that, now we know when. Well, okay, the intersection point, is that when we want to start? No, I think the intersection point is not interesting here. It's only interesting when we actually encounter a solid here. So actually this would be the intersection point. It's the start position subtracted by the last split, which we should have. Branch, splitter, normal, and we scale by the radius. So we can calculate the intersection point. If we have a starting point, we can calculate the intersection point from that. Okay, and then we have the center here. This is kind of the midpoint. I'm gonna call this mid instead. And so this goes up to the midpoint. And then we have the same radius, same acceleration, same velocity. This one though is different, because now we need to say that this is the node where we're split. The node we're looking at is the wait, which node are we looking at? Oh, we need to know the sides. So this would be the start side. That's the same. If we get an intersection here, we simply return it. Otherwise, we return the other half, which is mid to end, same radius, same acceleration, same velocity. This one again is node, this one is the end side, and this one is the that. There we go. Okay, now we need to calculate the start and the end side, which depends on, we could pick either, I mean we have these, actually we don't have these. Okay, so we do need these anyway. I'm gonna put this one here so we can use it over here to calculate the start side. It's going to be is. So if the start position is in front, the start side should be the front side. Otherwise, it should be the back side. Okay, and then the end side is the same thing. So if the start is in front, then it means the end is in the back. And then otherwise it's the other way around, because there are always some different sides here. Hello, Aryan Singh, what's up, what's up? And of course, here we need to return each section point. And all right, so I feel like I'm doing a whole bunch of stuff and we're not testing anything, because it's this whole like calculation that has to be done. Everything has to be done before we can see the result. But hopefully, usually when I do things like this, there's a whole bunch of issues that we need to fix. But let's see what's gonna happen. So last thing that we need to do is we need to calculate the distance line. Good name for a function, and I'm gonna copy that. So we need a function here that returns a scalar, and this is some kind of line definition. The line definition is, I mean, it's basically it's like you take the line, the wall segment line, you rotate it 90 degrees and then align it with the center of this player circle. Or you just take the normal of the wall, extend it infinitely, and then align it with the center of the circle. You take the normal of the wall, you take the center of the circle, and then extend a line from that. So we need like the normal, we need like the direction and the position, I guess. But how, but how? And then we need intersection point. Okay, let's see if we can do this with some. This feels like elementary math stuff. Geometry. So let's get the normal. So here's, wait. Why is it like splitter P1, splitter P0, splitter P1? And then line 1, line 2. Okay, we get the normal. This is the direction of the line. And then we need the position of the line. Okay. And then we need like the wall. I'm just gonna say wall start, wall end. Just because that's what we had there. Okay. Now, imagine that we have this position and then we have a line along the normal in an infinite line. And then we want to find where does that intersect with this wall here. Which should also really be an infinite wall. So really, we can take... So actually, let's call this direction 1, position 1, direction 2, position 2. Like if I was to place this in an equation, usually I was thinking about lines like this. You have like, let's have like, you know, y equals kx plus m. So that's line 1. Let's do like, you know, this would be, all these would have ones, so a subscript, and then this, and then we do like 2. And then to find the intersection point, it's like when are they equal? Wait. But there's 2 dimensions. Wait. Yeah, if the y's are if the when, okay, so when is x1 equal to x2 and these equal. When are both of these conditions true? That's what we're trying to figure out. So I guess x1 equals x2 is no, another way is no, it's not when the x are equal. Wait. Why am I having such trouble with this basic elementary stuff? Okay, so if I'm trying to do some substitution here, but I mean we can say that x1 is equal to well, it's gonna be like y1 minus m1 and then divided by k1, right? And then x2 is the same thing, except everything is 2. I feel like I'm like overcomplicating this. And then, you know, this needs to be equal to this. Wait, what the hell are we even trying to figure out? We need a point when they are equal. Okay, let's do this instead. Let's think about functions. So function of x, so function 1 of x is equal to it's going to be like kx plus m, k1 plus m, and then this is the same thing. And then we're trying to figure out when is f. Yeah, so now this is different because we have like x is common here between the two. Right. I mean, we could have probably done the same thing. So basically we just need to check when the y's are equal, question mark, on the same x. Yes, yes, yes. Okay. That's the thing. That's the thing. Oh my god. Okay, so k1x. So basically this needs to be equal to this. Or any other kind of equation you have for the line. We have these things which we want to turn into this, or try to figure out how to use this to map these infinite lines somehow. I mean, we have position, so that would be m. We could substitute m for position y. And then we have like x. I believe there's also the face or whatever it's called, I think. So it's like if, let's say the k is 1 m is 0, so that starts at 0, 0. But if this is 1, we should start at 0, 1. So if x is 0, we should end up at negative 1. So is it negative here? So this is 1, so we have 1 here plus 0, so that's actually 1. Actually, is this negative? So that aligns. But then if k is 2, wait, if x is 1 now, 1 minus 1 is 0, plus 0 is 0, so that checks out. And then, but what if k is 2? That means that at 0 you would have no, I think that does this check out? If k1 is 2, then at 0 you would be at negative 2. At 1 you would be still at 0 then, because this is 0. Yeah, so that checks out, I think. All right. Okay, so that's the so we can plug this in for, so this is y and this is x from position, and then this we need to calculate from the direction. I think it's just gonna be y over x. So essentially you have like k1 y over x, unless x is 0, which means that we're going straight up or down. And I guess actually we need to add, sorry, yeah. So if it's 0, it means we should just pick, wait, then the k is 0. Is it 0? No, it goes up. The direction goes up. So it's probably like something like infinite or something. Because everything is on. Yeah, this is weird. Like x doesn't matter at this point. Wait, or does it? God damn it. Okay, well, if we want to be able to compare here, what do we do? We want to find x. So basically we want to break out x from this equation here. So we take, so we have like negative m1 and then we divide by k1. Oops. We can distribute it. We're kind of baking this in. Wait, no. I feel like I'm going the wrong way about this. Yeah, I don't know. I'm too bad at maths for this. Because it's like this x is both in here and in here. So we have like essentially we have k1 times x minus k1 plus k1 times p1 k2 times x minus k2 times p2. Actually, we can do it like this, maybe, and then we remove this over here, flip the sign. We take u over here, flip the sign. Gonna put u at the end. So now we have like k1 times x minus k2 times x. So we can, okay, so we can, wait, no. I was thinking something like x minus x, that doesn't work. The common factor is x. Wait, yeah, what the hell? So like k1 minus k2. And then we just divide by that. And that's the... And that, what the hell is that? Wait, this is the intersection. What the hell? I'm trying to calculate the distance. Oh yeah, but we need the point along the line that is the intersection point. Yeah. We need the intersection point, and then we calculate the distance between the intersection point and the original point that we want to check against, right? The center of the circle. So I'm just thinking if you could simplify this here. Probably not, whatever. Okay, so if we can get these values, but now k1 is weird because if x is 0, then it goes like straight up or straight down. So what the hell is k1 then, if it's straight? Like if it's infinite, then this would be like 0 or something. Which means x is always 0. But that does not necessarily... That's not necessarily the case. Okay, maybe this is wrong at the first start. We can't actually say in terms of x where this point would be then. So this whole calculation is useless. Okay, you know what? I'll give up. I'm just gonna ask our dear old AI here. Actually, you know what? There's an even easier way. No, there's not actually, because Raylib doesn't work with infinite lines. How to get the intersection of two infinite lines. Okay. Vertices of the first line, so it's like start and end. Right. So it's just a way of like defining a infinite line based on that, and then you have like, yeah, so they're using like fancy stuff like cross products and stuff. I don't really understand cross products. I need to study that first, I think. Okay, so P equals P1 start. So you have two lines here, and R is the length, or the, well, yeah, the relative. Okay, Q is the number 2, S is the relative 2, T is the thing we're looking at, or T is, I don't know, well, times R. Okay, so it's like where along the first line is the intersection point. So we do cross product of the relative position between or from point 2 to point 1 and the relative line 2 over, so we divide that by cross. Yeah, I'm not gonna pretend to understand this because I don't even know what the cross product like intuitively is doing here, and that's the intersection point. So cool. And it's like, yeah, there's no like, if this is between this or this, then we don't have an intersection point. We have an intersection point and we can calculate it like this. So let's just copy this here. Delete this shit. Put this in here. Remove that. Comments. Alright, so we got like, so actually, so okay, I mean, we could get these by adding, so it's like we have P is just position 1, R is position 1 end minus start. I mean, that's basically just direction, actually. We could say direction, like it doesn't even matter. Like, yeah, that's direction. And then, you know, same thing here. We already have these. Q is position 2. S here 2. Oops. T is gonna be, so it's like Q subtract with P, and then we do cross to S. Wait, do you not have cross? We have cross. We have cross in here, I think. Yeah. Okay. There we go. Cross. And that gives us a scalar, yeah, so we can just divide that with the cross between R and S. So there we go. And then this is the intersection point. It's gonna be P plus T R scale with T. And that's the intersection point. And then we shall return the distance. So I think the first... So the second one is the wall. And then the first one is the circle. So position 1 should be the center of the circle. So we simply want to return the distance to I. Okay, so the first dir is going to be the branch normal. The position is going to be the start position. Then the other one is the direction here is going to be a splitter vec. And then this is the splitter P0 is the start position. Same thing here, normal, and then the end position. Okay, I think that was the last thing. All right. Yo, Penguin, what's up? What's up? Hope your sports is going well. Okay. Okay. So I mean, yeah, we have the sweeping of the circle, the sweep circle function. So we can use that now instead of the ray cast when we check for collisions and stuff. So let us do that. Right, so instead of casting a ray here, we are going to sweep a circle. And we still have a start and the end, and the radius we need to pass. I don't really know what the radius will be, but we'll define something here. Player radius. Let's use 1 or maybe 0.9 or something, I don't know. So we can, no, actually, let's just do 1 and we'll figure it out. Okay, and then you need, as well as that, we need acceleration, which we have, and then we also need velocity. Yeah. And yeah, that's it. And then we're almost there. Let's see. Okay. So now we have a circle intersection point instead. So I think that this is enough for us to see that we should like collide with the circle physics now instead. Oh man, we reached unreachable code. Why does it take so long to exit here? Yeah, reached unreachable code. I wish it said where it was. Oh, it's over here, 135. I see. Interesting. Oh yeah, I forgot to change one of the absolute checks here. This one, abs. Yeah, it is actually this one I forgot to change. So that might be the reason. Are you going to push the code after this one is done? Oh yeah, I forgot to. I think we have the repo, right? So yeah, I can push the code. So now we're on 151, so we have another place that's unreachable. T is okay. Well, so my understanding of this was incorrect then, which is kind of weird. I mean, yeah, but okay. Well, I guess in the case where we're never going, it's basically we don't actually collide with the wall at this frame, which means we should probably just return. Yeah, okay, so we just return null, I guess. It's kind of weird because we're not in a leaf, so we can't really do that. Although it feels like this check, it feels like we need to do this check again here. In that case, but what if we're over here? This doesn't make sense. I guess we'll do like if either is on front or if either is on back. We'll just do that. Like if the first, okay, let's just do this. We'll do an if else. Can simplify this. Oh? Okay, I guess we went further than we should have. Oh wait, this is stupid. We get like the intersection point. Attempt to use a null value, right? We get the intersection point. But really, we should return the player position when the intersection happened. I mean, we probably want the intersection point as well, so we probably would want both. So what if we add I guess this could be like object position. which is like, where did the object I guess it's also it's actually nullable. It's only if it's intersecting. Intersection object position. Let's just call it object position because it's the intersection info. Cast ray. So here we return the start position. Object position is the start position as well. But down here it would be yeah, it's the start position as well. So there we go. But the intersection position is calculated through a different, yeah, right. So like start position X, 0, start position Y. And so actually we don't care about the intersection point again. It's actually going to be the intersection info dot object position, but now it's yeah, it's vector 3. Wait. Wait, this doesn't... That was the wrong thing. Right, we don't even use the intersection point here. We're like calculating a new velocity, so we're kind of backtracking the player, and we're using a new velocity depending on where we collide. So that's strange. Why would it allow us to continue in that case? I mean, of course, there's probably something wrong with the calculation, and of course we reached unreachable code. $138. This again. Okay, that might have something to do with reaching a corner. Oh! I saw a little bit of... Did you see that? If we move forward... Okay. I saw that it actually did work for like a second. And it looked like it slid along the wall. But then, you know, something else went wrong. Okay, 113. We have a little bit of hiccups, I guess. Maybe this calculation is wrong here. Well, I guess we could use this calculation to figure out if we're already behind or in front, actually. Yeah. So let's say so yeah. So let's do that. Actually, let's remove. Well, let's do this. Okay. And so here's like if t was less than 0, that means we're in. If it's more than 1, it means that we were in front and we don't collide this frame, so we should go to the front, but with the same stuff. Otherwise, t is less than 0 and we go to the back, this should be unreachable. Should be unreachable. But here is like we need to know if we're on front or back still. So actually let's calculate that. Well, I guess we can do this. Oh. We reached unreachable code like immediately. Okay. What the hell? 138. I hate when you get into that weird thing. Okay, so it's this thing here. Is it like if the velocity is 0 or something? Yeah, because there's a bunch of times in there. So I think this becomes 0. So this can be 0 now. So what do we think about that? What did that mean? It means we basically were not moving along. We're either not moving at all, or we're moving exactly parallel to this wall, which means we are never gonna hit it, which means we need to do this calculation. But it's also like we could be like in the wall perhaps from the start, maybe, or maybe not. Yeah, we could technically. So what do we do then? I guess we will. Do we split then? Like in both sides? Or do we just say that t is... No, because yeah, then we don't know if we go towards or behind. I think maybe we'll do a split here as well. And but we don't need a midpoint. We don't have a point at intersection. So we don't have a midpoint. So this doesn't matter. We just do like start to end on both. And we just pick, this is just gonna be the front. I guess we could calculate that. And use that as a thing. Yeah. Okay. But we don't need a midpoint. Wait, no, that's wrong. What the hell? Just started gliding. And as soon as I try to move, we get a crash. Okay. So yeah, so essentially if we're standing still, this is true, and it goes in here and tries to check. And we split on both. We're either standing still or no. Okay, I think that we could send the thing off to a child node instead. I mean, we could have an optimization to check if the velocity is basically 0, then we just skip everything. Maybe. Because then we would know. Okay, whatever. Let's just say Yoko guy, what's up, what's up? Sorry I haven't had time to check out your stuff there. There's a bunch of stuff happening. Let's see. Okay, so essentially the idea is that if we're parallel to the wall or not moving, we only need to know one of the points, because either it's going to be end and start at the same point, or they're going to be on the same side. So we only need to calculate one of them. And once we have one of them, we know which child to send. So we don't need to split, actually. I just realized. So we just need to sweep the circle, same positions, same radius, same acceleration, same velocity. This is the same. The node is going to be the side, and then you're the same. And side depends on if it's on front, then it's going to be the front, otherwise it's going to be the back. I think that's better. Not sure why we were gliding the other. Okay, so as soon as we try to move, we get some issues. So 113 over here. So last split is null, apparently. Why would we even be in a solid though? That seems very, very wrong. How's the BSP going? It's going, I mean, you know, slowly but surely. I mean, I'm confident that the thing we're trying to do is possible. It's just trying to figure out how and making everything work. Anything is possible. No, but yeah, we're trying to figure out how the player, or I'm trying to figure out the player's collision against the wall is now a circle instead of a point, and we're just trying to make it not crash and everything. Are you creating any game engine? Not really. I mean, I'm more creating like kind of like a demo that I'm personally using to learn BSP. But what I'm thinking is like, I want to get this. What I'm thinking for this project is I'm gonna get this player collision, like circle collision, working. And once that is done, I want to kind of, you know, make it look a little bit nicer, like change the wall textures, maybe try to add like floor and ceiling textures. That should probably be pretty easy since we can just use the rasterization or the rasterizer things for that. Maybe lighting, maybe a shader, maybe, and then also maybe like dynamic objects so that you can actually shoot like enemies and stuff. That would be cool if we could get there. So once we have all that in place, I'll probably call it for this project. I won't like make, you know, anything more than that. But it is fun when you get some like velocity and productivity and you know, you get to a kind of a plateau where you can add a bunch of stuff. So that's kind of fun. I mean, we could do it in this stream, like change the wall textures, get some floor and ceiling, and maybe. But yeah, I just want to make this work here. Is this similar to Swing in Java? I have no idea actually. I've never used Swing. I've only heard it in name. I've heard Legends, no, but I haven't. I don't even know what Swing is, to be honest. Is it the? Actually, you know what? I think I remember something from the university. Is it the Windows library for Java? Like when you can create like Windows and UI and stuff, and layouts. I seem to remember something about that. It's like similar to how a web browser, they had like these different layouts and stuff, where you could divide the layout in and do similar things, but you got this distinct Java feel to it. Okay. Yes. Okay. Yeah. Yeah. I do remember that, but that was a way back when I went to university, like 10 years, 12 years ago or something like that. Yeah. All right. I mean, it worked kind of. I mean, it was similar also to the Windows thing that was available at the time as well, or before that, even. I don't think it's the. It was. I'm thinking about the Foundation thing, Windows blah 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 Foundation. I don't remember what it's called. It was. I remember some kind of window that when I started learning about like Windows, like making a window in Windows, I was using some kind of weird, I think it was Visual Studio, and then you get like a mix between designing a window with dragging buttons and stuff. And I remember this dotted grid that you could snap things to, and yeah, I have no idea about how to like make things look nice at all, and different layouts and stuff. And then there was the code view that you could then code in. I forgot what the language was, but you basically got, maybe it was C#, maybe not. I don't understand. I don't remember now, but yeah. Good old swing. I remember learning grid layout, stop doing position calculations. Yeah. Yeah, having a way to like automatically calculate positioning and stuff is better, I would say, than doing like manual updates of everything if you change one thing. You do OS stuffs too? What do you mean? Like I've done like, you know, desktop applications. I've not done any. I'm not done anything like drivers or operating system stuff. You use Zig in job? No. I've never used Zig in my work, or well, where I work. Maybe in the future, we'll see. But I think it's more like I mean, it can be used in a professional way. It's just that right now I feel like, for me personally, it's more like a fun language to use. Because, you know, if you're gonna introduce a new language in your workplace, then everyone else also need to, like, everyone else that's working adjacent to you needs to know about that as well. Which is kind of weird, because where I work now, they have maybe like, I don't know, 5 different languages or something, which is kind of weird. And then they have like free reign of choosing a bunch of that stuff. So, but maybe that's the issue. I don't know. It's like people have their little islands where they can be kings or queens or whatever, and rulers, and you know, decide on technology themselves. But then they have some kind of They have to integrate somehow with other people as well. I got 100 subs on my channel yesterday. What? Nice. How did you manage that? Did you buy it? No. Sorry. That's insane. It took me like, I don't know how long to get 100 subscribers. Did you upload a video or something? Did you go viral? Okay, what are we trying to do? Started doing LeetCode. Anything but people watching. Do you mean that bots are watching, or what do you mean? Or is that maybe it's a popular, like, maybe LeetCode is very popular? I don't know. LeetCode content. Or maybe you just... Oh, you didn't get 100 in... Okay, I read that wrong then. Sorry. Oh, you had 80 subs. It took 3 days to reach 100. I mean, wow. I mean, for me, it took like... I mean, I had this channel for, I don't know how long now. 2 years? Almost. It's approaching... No, not 2 years. Wait. I mean, it's 1.5. At least. Maybe it is 2 years. No, it's 1.5. Something like that. And I have like... So, in 3 days, you get... So I almost have 600 subs now. So let's say it's a sixth. So in 3 days, it took you 3 days. So basically, how long will that give you? To take times 6, 18. So basically 20, let's say 20 days to reach the same level as I've done in 1.5 years. You think the algorithm pushed your channel by mistake? Or you just have an aura that draws what content, so you're doing like LeetCode content. Maybe you have like a, super programming aura or something that draws programmers from all corners of the world. Okay. What's happening here? I try to move and we crash, right? Try to use null value. Oh yeah, it was the split thing. Yes. So it splits over here. Yeah, I mean that makes sense. But then why would we enter a solid? That does not make sense. We are not supposed to be in here actually. That does not make sense at all. Are we taking the wrong thing? Is this the back or the front? Maybe it's the other way around. Okay. Wow. We just moved straight past that wall. You stream for 5 hours. Yeah, I've also noticed that if you stream for longer hours and more consistently. So if you stream every day, or like I couldn't stream like every day. I can stream like when I had more time. I could stream like every weekday for 5 hours, 8 hours every day. That pushed my channel, like that pushed the channel so that I got way more, way more viewers and way more watched hours and stuff. So, it was just a matter of just, I mean, it could have been something else, I don't know, but it felt like when I was doing that, I got way more numbers. But then I was busy doing something else, so I took the time down a little bit, and then I lost a lot of numbers there. So okay, you've been doing it for the past 30 days? Yeah, so if you just continue with that, if you can, I mean, it's just gonna continue to push that. So if you want to grow if you want to grow the channel, that seems to be a good way of doing it, or at least like one. It's better than not, like, it's better than, I mean, either you go viral, I guess, or you can also do like better content, I guess, as well. I don't know. I don't really try to think about the quality that much. I just try to get on here and try to do things that I think is interesting. Anyway. But yeah, I definitely noticed a huge difference when getting on like everyday streaming for longer, consistently. I'm planning to continue this until I land a job, then I won't be able to do longer. Yeah. I mean, yeah, so then you've solved your problem, basically. You have a job. I mean, if you're lucky, you can maybe, or lucky, and I mean lucky, but if you're I guess a combination of lucky and work hard, you might grow your YouTube to maybe get some money. But I don't really know how much you're gonna make. Like, I haven't even reached the point where you can accept donations, so I don't get anything from like ads or anything from YouTube. Because you need like, I think 4,000 watched hours in the last year, which doesn't really, it doesn't really sound like a lot. It depends, of course, how many are watching. Let's see what happens. Yeah. There's always hope. You never know. That's the thing. You never know. All right. Okay. So let's go outside of these for a little bit. See if something happens. No. Let's go. Okay. So it weird. It's like I could go in, but then when I go back again, it crashed. Maybe I was standing in the wall. So it's like I can go in. Okay. So as long as I go straight, I can go straight through. What about the corner? Okay. But if I go here and then back, it works. Wait, but then I go forward over here and it crashes. Wow, that's weird. Okay, so it leads me to think that maybe something is like the other way around with these front and back stuff. Maybe. I mean, we're not getting collisions. You should start adding learning BSP day to continue to do. Yeah. Yeah, you never know. Yeah, I mean, I've been thinking about like adding more, you know. Couldn't you use AI to kind of summarize the video or something like that? Man, I don't understand what's happening here. Is on front. Maybe it has to do with like the last split. The last split is used to figure out which wall are we actually colliding with. Yesterday, one of Microsoft's employees joined my stream and said algorithm shown my channel to him. Okay. I mean, it might be that the topic, like what tags were you using? It might be the topic of the... No, this is definitely wrong. The topic of the video might be like hot right now or something. Yeah, you'll be streaming from 2024, yeah. I mean, congratulations. Reaching, like, yeah, because I remember, I think 100 was like a huge, it felt like a huge milestone. And then 500 was also really nice. But it also feels like the longer you do it, the more, like, just being active just goes upward, so eventually you will reach some point, you know. I made a single title and description, just update the day alone. Okay, yeah, I understand. I might do that. I mean, it's probably... I mean, I could just go into the videos and update them after the fact. Maybe that... It's also, like, interesting because it seems like YouTube pushes things that are new. Like, if you start a new series or if you start a thing that's maybe unusual or something like that for your channel or something. I don't know. It feels like it pushes that, because you always get like more, like you see on all the, maybe this is different, but you see on all like playlists on YouTube, and you go to the first one, always has like a lot of views, and then you go to, or well, depending on whatever, you know, and then you go to the next one, which has like about like half or something. It follows like this famous curve, I think. I don't recall what it's called now. There's like a curve that kind of scales down. People join Discord today. We'll take a problem solve individual now together. Okay, cool. Awesome. Can you help me with this problem, code guy? Because I'm trying to figure it out. Yeah, we'll see, cold guy. You know, it could go. I mean, it's always you have to think. You have to always think about you have to think realistically as well, and not be disappointed too much if things don't go your way. What's the issue in the code? Well, I don't know. I mean, yeah, that's what I'm trying to figure out. So, so what we have here is, you know, we have our BSP. We have a way to... Oh. Oh, I see. Wait, that was actually a clue. I think right now... Oh, I see. I think I know what's going on with this specific crash. Is that I can move... I think as long as I move in a continuous motion like this, but as soon as I stop, I don't even have to be in the wall. As soon as I stop, or just move, I guess, or just move like if I move and then stop. No? Move the other way, stop. Man, I really thought that was the issue. Maybe I have to move in parallel. I think DSA will be a piece of cake you can crack. Mang and Fang, easy man. I don't know what you're saying. There's so many words there. So if I do... Yeah, there's definitely something weird going on with the calculations here, because it thinks I'm in a solid, which I'm definitely not. Why does it take so long right now? There we go. Okay, maybe we'll check like this. If velocity length squared is less than epsilon, yeah, the length should be absolute, so we return null at this point. That might fix that issue. There might be another issue where the velocity is like very large, or not the velocity, but some kind of calculation that becomes very large or something. So this should short circuit if we're standing still. We have yeah, if we're standing still. This shouldn't exceed the velocity though. Hey, yo, 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 yo. Can you update the title, Learning BSP Day 2? Well, it's not Day 2 though, it's more like Day, I don't know, 10. Let me check actually. So we've done like 1, 2, 3, 4, 5. Actually, it's Day 6. Is dot product equal to the product? Short answer is no. Long answer is no. There's like, because it's a vector, there are multiple components. You have x and y, possibly others as well. So so the dot product is not exactly, you know, a product in that sense. It's more like, to understand like dot product intuitively, I suggest you would watch like a video on it, because it's hard for me really to explain. But basically, you have two vectors, and if you do like the dot product on the vector, you get a scalar, which is just, you know, one number. It's a number, normal number, that represents kind of how far along this vector you go if you use this. Yeah, I can't explain this. I did update. Is it not, has it not updated it? I updated it. It should be updated. Where's the stream thing? I don't know. It should be updated. If you, maybe you need to refresh or something. Okay, you know what? Let's go back, do this, and we'll see the whole trace here. So we're going, whoops, no, I need to do it again, sorry. Yeah, it seems to happen when you go like back and forth and you're, yeah. So we got like 84 collision, and then a whole bunch of 159, and then 150. So 84, 159, 150. So 84 is the entry point, I would say, yeah. And then 159. So we're actually over here, which makes sense because we should be like in front. But we're taking the back, so that doesn't make sense actually at all. It has to be this. And then it was like 100 and something, probably here. No, it's there, this one, yeah. Whoa, but now I could actually move. Okay, now we're in 161. But now we're over here. This doesn't make sense. What the hell? I just switched this and this. And now we're going in here instead of in here. Okay, I think maybe something is definitely wrong with this calculation here. Because we shouldn't get in here. We should actually not get in here at all. I don't think. No. Well, maybe actually. But then it doesn't make sense to go back that many times. No, that doesn't make sense. Yeah, I updated the title. Maybe it's not as fancy as your suggestion there, but I did update. Does that actually help? Like having, like, I don't know, full grammar. I don't know, I haven't really experimented too much with that. Like on titles. I mean, maybe we calculate if t is, so let's just do, let's do this. Let's do like else and we get the side depending on if we're in front. So because essentially if we go down here we should be either in front or behind fully. So we only need to calculate if one of them, if we're in front, and then pick the side to go if we're in front or behind, and then continue down that path. Oh my god, that almost looked like it worked. Like it kind of works. We get some phasing. Okay, we get the same weird thing where we go back a whole bunch and then fail. Wait. No, it's this one. But wait. See? It's like when we stop. Oh. It's fake. It's like when I stop, I kind of slide along the wall. You see? But when we get too close, It's gonna break. Yeah. Okay, now that we don't do that. But now we, okay. Okay, I think we got rid of the weird bug where it crashes, but now we don't have any collision at all. Great. Is it some sort of building you're building? No. So this is the kind of, this is just a level here. So I've defined like two, I guess like, you know, squares here, that, which is the level. It's not, you know, it's not like I can build in the game here. The arrows here is more like, it's saying like the green, okay, so the green arrows and these green lines here are part of the same thing. So that is one wall segment here. And when they're green, it just means that we're now in front. So the game knows that we're in front of this wall. That's why it turns green. And the red ones are that we are behind that wall. So when you turn the corner, you can see it turns from red to green because it knows that, you know, we're now in front here. And so we can kind of use that information if we're in front or behind something to know, well, for one thing, we don't need to draw the wall if we're behind, because it's gonna be like automatically like obscured by something else. So we don't need to draw the thing. So that is one thing. Another thing, and this one is also different because this is the root node, so it's purple instead of green here. But the arrow becomes green and red depending on. So this is the root node. It means it's the first node that we're checking for that's where it's kind of like the we get like an infinite line almost here, or like, well, the line is like perfectly aligned with my vision here, so it looks a little bit weird. Okay, but yeah, it's like we're dividing the world into different parts. And you can see on this side, for example, we have two segments. So we have one over here and then we have one over here. This is because it's split by this root node. So this root node, this wall aligns perfectly with this line over here because it's splitting the whole world in two. So each segment here splits the world in two. So this splits the whole thing here in two and over here. And then it puts all the nodes, all the parts here that are like on this side, on the left side of this split, it puts into the front list, because this points over here, so this part here is in the front, and then over here, this part, all the things that are behind, to the right of this line, are put in the behind list of this node. So this node, like, it splits the whole world in two, where now we have a bunch of segments that are in front and a bunch of segments that are behind. And that is how BSP works. So so that, and then that information is used to optimize things like collision detection and finding. Here we're finding which points, when I click, which point am I looking at, basically, along this wall here. So we're using BSP for that, and also for, like, I'm trying to implement for player collision as well, using a circle instead of a point. So we already have point collision here, where you can find, or a ray trace collision, but we don't have like circle collision. So that's what I'm trying to do, which is not yet solved. So that's what we're trying to solve here. And I think we've gotten a little bit further ahead, but still, I'm not sure what is going wrong. I mean, we could focus on adding more debugging information and try to get more information to understand how this algorithm is played out. I'm just trying to figure out how we can do that. So maybe we'll do this. We'll go to input and we'll add another one here, shooting alt. So my idea is that we have a shooting thing, which is the red dot that you saw. When I press the left mouse button, we get a red dot. That is using a raycast, so it's basically just a line that you shoot out and you see where does that intersect, which BSP is very good at detecting. The circle though, which we're trying to implement, I'm gonna add another one, which is shooting alt, which the idea is we're gonna shoot a circle instead with the right mouse button, and the circle is going to intersect with the wall, and we're gonna see if we can show the information there. So let's see, I think it's in main, we have this thing here, and we'll do shooting alt map. What do you mean map? We could probably make a map pretty easily with this actually. It's just like the Doom map. It's like a 2D top-down map that you can like just render straight up, just the lines and everything. Alright. So instead of casting a ray, we do a sweep circle. And we start at the camera, we end at the end. We have a radius. I'm gonna pick 1. Acceleration. I mean, you know, the acceleration and velocity is kind of weird because we already kind of have, you know, we have a start and end position. We don't have acceleration and velocity. I mean, yeah, maybe that's the issue. Maybe we need to only worry ourselves about acceleration and velocity and not actually put an end position in there. But let's just figure something out here. Actually, instead of making the end, we'll make like acceleration to be, I don't know, it could just be 0 for this. And velocity is, so velocity is going to be, because we need some kind of direction. So it's basically going to be the camera direction, which is the target. And then I guess we scale that by something, I guess 1,000 or something. I mean, we don't really need that much. Let's do 10. We could normalize. Wait. Yeah. We normalize and scale it to 10. And so the end would be, you know, position plus velocity. Yeah. So it's like an instant thing. And so here we have acceleration, we have velocity, we have the root node, and intersection info. And so we get the intersection point. We could reuse the hit cube for this. That's fine. We could introduce another hit cube, like object cube. Same thing. So we got the hit cube at the intersection point, and then we have the object cube at intersection info dot object position, which also should be should work there. Okay, so we have this one, and then we have the alt, which doesn't work. Did I make? Okay, let's try scaling it up a little bit. Oh, I saw something. Okay, let's change the color. So let's change this to, I don't know, green. Make it a little bit bigger. Okay. Interesting. It's all way over there. Also, when we do this one, I want to basically keep it around for a while. Okay, so basically when we click here, it's showing something over there, which makes no sense at all. I mean, I guess it makes sense in some way. It's like it always goes to the right for some reason. Very strange. So the red is the intersection point. This is the center point of the object. Why is it down there though? That's weird. You should have the same. Oh, this uses start.y, right? Which we don't have. Okay. I thought that was 0. Is the dimensions flipped or something? What the hell? X and Z. Okay, another thing is let's get rid of the end position, because yeah, that we'll just use acceleration and velocity, or we could get rid of acceleration and velocity and just use the end position. I guess try to figure out how to calculate that instead of passing these. But then we need to figure out this algorithm here, or equation here, which no, well, I mean, we could just say that the velocity is equal to the difference in the positions, and then acceleration is always 0. So solved? What do you mean? It's not solved. Or what is solved? So acceleration is 0. So I guess this is always going to be 0 subtracted by splitter mid. So it's going to be like splitter mid. Let's do this. So it's going to be like splitter mid negated, and then dot product against the normal, and radius minus that. Something about this equation seems weird to me, but okay. And the denominator is velocity, where the velocity is simply the difference of end position subtracted with the start position. And now we don't even need these two. We do need a radius still, of course. Alright, we need to calculate the velocity over here. And we need to... So when we send this in here, we remove... Oops. Remove these two. Oh. Yeah, this also could be weird, like the midpoint is not great either. The midpoint is basically we just take start position, add velocity scale t. We don't have acceleration, we don't have velocity. So what do you mean? What is solved? What do you mean by solved? All right. Oh, camera, There we go. There we go. And this. All right. Yep. Still nothing. This still works, but oh, I mean, we get something. Over here. When we're going like over here. The hell? Yeah, something is very off with a calculation. Maybe it's the T that's wrong. I mean, given that we got this algorithm from, or yeah, the equation from AI, maybe that's a sign that it's not entirely accurate. But what if we just search for intersection point of sweeping circle online? Okay, it looks like it actually gives me like an entirely different answer here. Find an intersection of a sweeping circle and a line involves identifying when the circle's distance to the line equals its radius. Intersection points are found by calculating the closest point on the line to the circle center, then moving along the line by distance. Find the intersection. One, distance calculation. Find a particular distance d from center to the line. Okay. Intersection analysis. D is more than R. No intersection. Line is tangent. One intersection point. The line is a second. Two intersection points. Find intersection points. Okay, but that is for like a circle that is still sweeping. If the circle is moving, you can treat it as a static intersection between a stationary thick line and a moving center point. Or by checking the distance from the circle's center at specific time intervals. Sweeping line. I mean, I think like thinking about it as time makes sense, and try to figure out at what point in time do we get an actual intersection. That does make sense. It's just is the actual calculation correct? I mean, I guess what we can do is, if we have the calculation, to see that if a circle is intersecting a line, wait, is this the actual answer? Line segment versus circle swept collision detection algorithm. Wow, this is exactly what we're looking for. Also, sorry about the flashbang here. Notice implementation can be found on GitHub. Search the username monkey toilet ladder for the repository. It has passed all test cases I've given it. It's pretty fast, with the most expensive function being square root no trig. Please let me know what you think of it. Background. There's plenty of information on how to detect if a circle collides with a line segment, but I have found little information on how to do this over a time step. For example, we have a circle that is accelerated through line segment BE over the indivisible time step. This is just a test case. I would like to test against any line segment. Oh, actually, yeah, the acceleration makes sense, because if time is involved, you would want the acceleration to be part of the algorithm. It's just that when we have to kind of sync as well, that the acceleration and the velocity is calculated correctly, or the position update is calculated correctly as well. Like it's calculated in the same way that this algorithm does use it. So accelerated through a line segment B over indivisible time step. This is just a test case. I would like to test my against any line segment. Wait, for example, we have a circle that has accelerated through a line segment over an indivisible time step. This is just test. Like to test against any line segment. I have thought of two ways of detecting this type of collision. Calculate swept circle test. Okay, so you don't actually know the answer. I think there's a few questions here. First, how to find the point on a line segment closest to a circle. Yeah, we did this one actually. Suppose the segments A, B in circles center O and radius R. Let's assume the segment doesn't intersect the interior of the circle. Then this is the same as the point on the segment being close to O. First, find the point x equals T A plus 1 minus TB on the line through AB close to O. Wait, what is T? You didn't define t. Oh, wait. First found a point. X equals ta plus 1 minus tb. To ab close to, oh, this satisfies 0 equals ab. Okay, so t equals a minus b times. Okay, so this is the relative segment, and this is the center of the thing relative to the end of the segment. And then is this the dot product of that? And then the length squared. Okay, I don't recognize anything in here. If t is less than 0, closest point is b. If t is... wait, closest point? Oh, I thought you wanted... oh, I see. So t is like where along the line. So you take like t times something to get... t times, I guess, the length of the line to get like where on the line it is. But if you have 2 points, you also get like if it's not actually on the line itself. So but it works both for infinite lines and for lines that has like a start and end point, or just a start point, or just an end point as well, depending on what you use t for. So if t is in between, the next lies on the segment and is the closest point. What? Oh, so x is the point. But where did you mention x? What is x? You haven't even said anything about x. Now here's x. Okay, so to find the closest points, we just break out x from this. Or you can also, I think you can use t as well to calculate the point. Can we simplify the collision detection by only considering the points x on the segment which is initially closest to the circle? I'm not sure if I understand your proposed method correctly, but I see. You're referencing like x over here. Maybe. Oh, whatever. I'm not sure if I understand your proposed method correctly, but I think considering only the point x is not sufficient. For example, suppose O is 0, 0, R is 1. So a circle at the center of the origin, we have radius 1. A starts at, so the line starts at 0, 2 and ends at 4, 2. So it goes straight up. No, straight to the right. Suppose this displacement of the circle is 4, 4. What? Oh, for the sweep, right. Initially the point is closest to the circle is XA, but the circle never touches X, but it does cross the segment AB. Yeah. But this assumes we're working with, like, if we want like start and end lines, like start and end points of the line. We're actually only interested in infinite lines, so it does simplify. We don't have to worry about moving around a line because we can't. It divides the whole space in two. Third question, how to find a collision point if it occurs? Unfortunately, so okay. What if we, instead of searching for this, we search for on an infinite line? Circle intersection with sweep line algorithm. Unfortunately, I'm still not strong in center. Sweep line algorithm. Yeah, I think I have. I already have like an automatic payment for this, so whatever. Sweep line algorithm. In computational geometry, a sweep line algorithm or plane sweep algorithm is an algorithmic paradigm that uses conceptual sweep line or sweep surface. Okay, this is not the same. But this looks interesting as well. Use a conceptual sweep line or sweep surface to solve various problems in Euclidean space is one of the critical techniques in computational geometry. This looks like one of those Voronoi things for constructing. Okay, so it actually is a Voronoi. The idea behind algorithm type, imagine that a line is swept, moved across the plane, stopping at some points, geometric operations restricted. So this, I mean, yeah, this is like the collision algorithm for the sweeping. If you have a bunch of bound AABBs and you sweep over one of the axes, you can optimize actually quite a bit. Comparing to a brute force algorithm, you optimize a lot using a sweep algorithm, and it's super easy to implement, and it doesn't require any kind of I mean, yeah, it essentially doesn't really require any bookkeeping or anything like that. You essentially just have like a couple of lists to keep track of things during the algorithm itself, but you don't need to build like a bunch of trees and all that stuff, like in quad trees and stuff like that. So yeah, that is actually a really nice algorithm, just for its simplicity and also its effectiveness as well. But anyway, that was okay. So that was actually not what we were looking for, but somehow you're saying that this circle intersection with sweep line algorithm, line segment intersection by omnipot, given n circles whether any two intersect. Wait, describe and analyze a sweep line algorithm to determine giving n circles in the plane whether any two intersect O n log n. So this is the same thing, like you sweep, but instead of ABBs, it's circles. I'm not sure how to do with circles actually. I've never looked at that, but AABBs is actually simple. I mean, you can turn the circles into AABBs and then do a sweep on that, and then do a brute force on the ones that are left. Maybe that is what they want you to do. I don't know. Let's try and make a complex thing into intersection. What do you know intersection circles? Okay, I don't think this is what. No, it's not. This is not the thing. Sweep line. It's not, yeah. I think it's like if I search for sweeping circle, it goes for sweep line instead. Okay, let's do a little bit of our own thing here. So we have the circle. Let's do like O circle center. R is the radius. Let's just do a constant velocity. Forget about acceleration. E is the circle center end position. Okay. They're doing some kind of weird normal cross thing, dot product. Was it cross or dot? No, there's no cross products here. Where did we do that? Oh, over here. Okay, and t is time. I mean, I guess we do need the normal because we need to know the direction. Yeah, okay. X is wall normal or segment normal. So we have the normal. We need a position, some kind of point along the wall. I'm gonna say W, so segment point. Okay, actually, let's just do circle velocity here. All right, see you later, penguin. What? What are you sorry about? Okay, so I guess, yeah, for some reason they wanted like D, like let's say D is the denominator. They wanted to take V dot for dot product and N. So V against the normal, because if, no, not the normal, no, just the wall. I'm gonna say C for segment direction. So the velocity against, no, wait, no, it is the normal, I think, because that is like, if this is 0, then that means then velocity is parallel to the wall. Yeah, that makes sense. And then what did the denominator mean? It was like, it's down here somewhere, or the numerator, I mean, radius minus, so whatever radius, whatever, but we take like some point on the wall, negate it, because it was part of the acceleration, like acceleration minus this, and then dot product that against the normal. Maybe this is kind of weird. What would this essentially be? This would be like so you got like the midpoint dot product and normal. This doesn't make any sense. Did I read this correctly? So radius minus acceleration minus W, and W is like, I thought W was like a point on the wall. The wall is defined by a point on the wall and a unit normal vector pointing away from the wall. Yes, W is just a point on the wall. So here they're doing like the point on the wall dot product with the normal. What would that be? Because it's like if we have a line, here's the normal. We have any point on the wall and the normal. We know like the whole line. Although this line is, it doesn't matter the start endpoint because it's like an infinite line. So imagine this going all the way here, whatever. This is an infinite line. And that looks so bad. Let's just do this. So this is the line. All the lines in this BSP are like infinite. So, which actually is nice because it simplifies a lot of things. So, what did we say? What did we try to do? So this one said it's taking some point on the wall, negates it, and then dot products with the normal. So if we draw this other universe here, and we have some point on the wall, so let's pick one point. We'll pick this point here. So the origin from here goes like up like this. So this would be the vector. So I'm scaling it down. So it would be like up here. This vector like this. And then the normal is going down like this. So what is the dot product of this onto this wall? It goes back like that. Wait, no, it doesn't. No, yes, it does. Except it goes like over here. Well, yeah. So it goes back over like this. So it's like some kind of negative number. See, this is the normal. And let's pick another point. Oops. So let's pick a point over here. So that's essentially, let's pick like a point that is straight like this. So this is just going straight over here. Now this one projects something like this. So it hits this kind of the same place. So does it always hit the same place? Like, what if we pick this point? I mean, it doesn't matter because a normal can be anywhere. But the middle, we just go up a little. Actually, let's just go straight up. This actually is different, I think, because this should project. Well, it depends on the position. It projects down like this. So it's still like, I guess it's like negative as well. So the negativeness, I think it depends on the relationship between the wall and the origin. Like if we move the wall below the origin, we get, you know, it rotates so that you get things like this, and then they're positive instead. So it doesn't make sense to me. What do you actually gain by dot plot, like taking the position of one of the walls? I think it's because it's like they wanted to know if the acceleration did anything. So if the acceleration was like up like this, it wanted to know what's the relative position of the acceleration depending on, like, from the wall, some point on the wall, and it's like something like this. So you get like this thing over here. Actually, the acceleration would look like this. No, it would look like this. And so you get something like this, yeah. So it's like, if this is positive, we're accelerating towards the wall. If it's negative, we're... No. Then you get this. No, that's still positive. Yeah, that's very strange to me. Unless I'm really missing something here. It's like taking the position of the wall into account. Depends on the origin. It's also like this one here. Let me show browser. This part here, we want the time where the distance from the player to the wall equals the radius r. So position of the player time minus w. So what is this calculation? It's like some point along the wall. It could be like almost infinitely long away. So the relative of that, and then we dot product that with the normal. I guess it makes sense actually when I imagine it in my head. It's like you have a sweeping point along the... You have a player position. Player position is over here, let's say. Okay, and then anywhere we point towards the player like this, you get these kinds of vectors. Right? So we get like this vector, we get this vector, this vector, this vector. They should all kind of angle downwards along the normal. And when you take the dot product of that to the normal, it's gonna project. All of them are gonna project like this, I think. Yeah. Okay, I see. So that tells us the distance. Okay. Okay. So the distance could be like, I'm gonna say it's like d0 or something. This is the distance from the circle to the wall. And then of course you can check if it's within the radius. So this would be the circle minus segment, some point on the wall, dot with the normal. That's really cool, actually. If it's correct, that is. Okay, I'll just BRB 1 second here. Right. Let's see if we can make sense of this. So that's a cool. I actually that's a really cool. If it's correct, I mean it looked. You know, we're eyeballing it basically, but yeah, AI tells me it's right. I just need to what's it called? Check these equations here and understand them to move forward here. Okay, so we have the distance from between the wall and the circle center. And okay, so now what? I was just wondering what that equation actually meant at the top there. And so what we need, what we want to get is, let's say player, you know, this position t is equal to, you know, O plus t times velocity, and we're just ignoring acceleration at this point. I'm just to simplify things. So this will be O plus TV, right? And so we could plug that in here. So dt would be pt minus w dot with that, which is equal to O plus TV, and like it was working with some kind of distribution thing with the dot product, and I don't actually know how that works, but the dot product is just a very simple equation. Where you take like A1 plus B1, no, A1 times, so it's essentially A dot B equals A0, I'm gonna use 0 index here, A0 times B0 plus A1 times B1. So I'm just gonna use the two-dimensional here, but you can have any dimensions, and I just add plus A2 B2 plus and so on. Okay, so this is essentially, you know, this is dot here, so we could just plug this in to get to like expand this, and but then there are like properties of the dot where you can essentially apparently do things like whatever they were doing here. In if we just, I just want to make sense of this. So essentially we have this now, ignoring the acceleration. We have PT, and according to this, PT is acceleration plus velocity, and ignoring the starting position, which I found was really strange. But yeah, we should have a starting position here as well. So PT is the starting position plus TV. Okay. It's kind of weird that acceleration is then almost like equal to a starting position, because that's the same thing. Okay, and then negative. That has to be something weird with that. Negative the point and then dot product. So it all makes sense so far, but then you say distribute the dot product, and it's doing something really weird here. So this is essentially like, okay, essentially we're just removing these parentheses, we're moving things around. So now we have like something like this, and then distributing the dot here like this. Also, it removed the scalar, the scaling, the factor here, and moved it outside, which I guess works if, well. So how would this look? So we have this. How would this look for this part here? So let's do an offshoot here. So we have, so A in this case is this part and B is N. So A0 would be this 0 times N0. I'm gonna do this, make it a little bit more compact, I think. And then we add this 1 and 1. Whoops. Okay. And then what is the so this part over here is essentially saying that we're dot producting two things. So we have like O minus this and 0 plus this 1 and 1, and then plus T times V0 N0 plus V1 and 1. So first of all, can you actually, because I was thinking like TV is, it was like this. Is this the same as this? Then you would have like, I guess it would be T as a scale like this, yeah. And then that's a common factor, so you can move it out. Yeah, okay, that works. Okay, that works. What about, I mean, I would assume this other thing works. I just want to see it for myself. I mean, hang on. So essentially this is the first one. This is O minus W dot N. This is V dot N. So essentially we could take, yeah, because this could be turned into, we just extract TV and then do this, right? Yeah, and then the same thing here. And there we go. Now we have the same thing. Okay. So distribute and then isolate T. Right, so now we need to break out T. So, I mean, we're doing the same thing as they are doing, basically. But dt, yeah, dt is equal to this. Wait, how did they phrase it? It's equal to r. Oh, I forgot about r. This is distance, right? So we need to know. Okay, so we need to know when is the distance equal to r, right? And to do that, we'll plug in this now is equal to r, and now we can continue here. So we'll take this part out. We'll divide by this. There we go. This tribute, yeah. What tribute? Okay, so t equals to this. Or wait, did you actually tribute anything, or did you just say that? Okay, so what I'm trying to say, I can't speak. I've been looking a lot at history stuff recently. I don't know. I find it interesting. I think that I'm kind of prepping myself into start working with my Metroidvania game, because that is going to have some kind of archaeology stuff in it. So it's kind of interesting learning about history, about like ancient civilizations and stuff. Tribute, the word tribute triggered my brain to start thinking about that. Probably also want to use like AI to improve the editor. Okay, t equals to radius minus start position. Wait, where did the velocity go? Oh yeah, velocity is over. Minus the wall, so relative position. Yeah, this is the distance of the. So this represents the distance of the starting position, and this is just a radius. So we can actually plug this in to kind of make more sense of this, I would say. This is the distance of the starting position minus r. So this, the numerator would represent if this is positive, it means the distance is greater than our radius. If it's negative, it means that we're already within the distance of the wall. So the circle is already intersecting the wall, or it's behind the wall. But then we divide this by this thing. So what does that represent? The velocity? Well, I think we already went through that. I think, but yeah, that's the denominator. So it's like, yeah, okay, yeah, it like determines the direction of a relative direction in relation to the wall. And that's t. So that makes sense, I think. Yeah, and if we added acceleration, we would get some other thing in here as well, but okay. So I think this looks correct then. I just want to I wanted to understand this, because we're dealing with a lot of shit in here, and sometimes it's hard to see where things go wrong. And I mean, now would be maybe a good time to be able to debug this, but you know, I'm not doing that. Hey, Dialog, what's up, what's up? Did you manage to understand collision with BSP? Yes and no. I mean, I think I have a thank you very much for the help, by the way, last time we spoke here on stream. You really, I think I was running out of brain juice, and yeah, I couldn't just, I needed to, some time off to kind of like sleep on it, so my brain could kind of massage this information into my consciousness, so I could formulate some thoughts about how this actually works. So yeah, I think, yeah, I do understand the BSP structure now, and the kind of some of the properties of the nodes and the lines and all of that, the planes / lines. One interesting fact that I think is interesting is like all the planes or lines of the BSP segments are like infinite lines, which makes them easier to work with, and they also, like, you get these leaves which then represent actual volumes or areas, depending on if you're in 3D or 2D. And I didn't understand that at first. Like, I didn't understand how it all was structured and how you would be able to use the BSP. But now I have a better understanding, and we've successfully implemented the raycast thing. If this still works here, I can show. So I can click, and it will. You have a dot on the wall, depending on where you look. So there we go. Which is really cool. But what we're trying to do now is we're trying to also fix so that the player is colliding. And I know you talked about the Quake, how Quake did it with multiple BSP trees using some kind of raycasting or whatever on those trees instead. But I'm trying to solve it using circle sweeping along the line, and not using like multiple trees, but I'm using like a circle sweep and trying to see where's the intersection point there, and then use that. But yeah, we'll see. So that's what I'm trying to do right now. So then once we have circle collisions, I can think about implementing dynamic objects as well. That is gonna move around like enemies and stuff. And like how to render those, how to... like rendering should probably be same as... we're just trying to figure out the order of rendering, I guess. And then yeah, collision detection for the dynamic objects. So what I'm thinking there is like keep having each object as a child in one of the leaves. Now they could be circles, so there could be like overlaps into multiple leaves. So maybe they can be present in multiple leaves. We'll see. But yeah, that's gonna be kind of cool. But yeah, now we're just trying to make this basic circle collision working. So yeah, it's kind of weird right now. It doesn't really do anything that I would expect it to do. You can see here, it's kind of, you can see here, if I press the left mouse button, we get this intersection point, which works.
if I press the right mouse button, it's like I'm sending out a circle instead to test this thing. I can see that it doesn't really work that well. If I aim over here, nothing seems to happen. I don't really know where the things are. If I aim over here now, if I stand here and aim over here, at this specific little spot, seems to be along this wall here, we get some kind of interaction here, but you know, it's nowhere near working, because what you're seeing is the red point is supposed to be the intersection point along the wall, while the green is supposed to be the center of the circle. Imagine a circle going along, like the circle has this radius here, so it goes around like this. We don't really see the circle. Maybe I should do a circle instead. Actually, make it more. Then I can recommend watching Handmade Hero Day 50, Basic Minkowski-based collision detection by Casey, where it explains collision detection using Minkowski sum for arbitrary shapes, but also circles. But does that involve like making multiple BSP trees, or is it, or are we using like the Minkowski sum in the collision algorithm? I'm just trying to do the most basic thing right now. Not specific to BSP, just general explanation. Okay. Yeah, I mean, I haven't even looked at the Minkowski sum algorithm. So maybe, I mean, maybe it sounds very intimidating, but maybe it's more simple than I thought. I don't know. Let's see. What did I think about? What was it that I was thinking about? So basically, I mean, the algorithm that we're using here is I asked AI to kind of give me an algorithm for sweeping a circle along the space to see where we start to intersect with a line. And so here's basically the algorithm for that. Now this is just calculating some simplifications here, but basically I have a bunch of, we have the circle, we have the radius, we have the velocity, time, and here's the segment information. So you have a point along the segment. This isn't really used, so we don't really need this. So you just need this, and then to get the time of impact, we have this algorithm here, and then you can calculate the position, the new position like this. You would get so position. So the new position is gonna be the starting point plus, you know, TV, where T is this T here and V is the velocity. So that's it. Minkowski sum greatly simplifies the detection. Are Zig doc comments support any HTML? HTML. I don't know. I mean, NeoVim doesn't support HTML. It's just text. I don't know about that. Let's see. It would be cool if NeoVim had, though, you could have like a links type rendering of HTML documents. I mean, that probably exists already, I don't know, but okay. So I highly recommend the videos talks about this exactly. Okay. Well, I'm yeah, okay. So okay, I mean, I think the theory is correct. It's just that I need to make sure that my code works with it. Yeah, Emacs. Yeah. No. I'm never gonna try Emacs because then I maybe get stuck in it. Although I don't really enjoy parentheses. So there you go. Let's see. Yeah, because if there's some weird issue. Somewhere. Like the issue we had with the Raycast before was that it didn't actually, like, we were building the tree wrong, in the wrong order, and then all of a sudden now the Ray started to work. So there was a lot of trouble with that. But you know, according to my logic, this should all work. I mean, the Raycast works. It's the circle thing that does not work because of some weird stuff. I mean, I'm thinking it's something to do with the front and back, how we move things around, how we descend along the tree, basically. So it's like here. This is basically like if we're moving, either velocity is very close to 0, but then we shortcut, we cut this short over here. So the only way we're in here is if we're moving basically parallel to the wall, and in that case we want to check, okay, are we in front or behind the wall? If we're in front, then we just continue the algorithm. We're walking down the tree to the front node, otherwise we move to the back node. Hey, Mutasimos, you joined late. Yeah, I have like maybe an hour left or something. I probably will end it very soon here because I'm running out of energy here. But welcome anyway. Man, if we could get this working, that would be really nice, because then I think it's gonna be smooth sailing. I won't say too much, but after this, I mean, it's bad to jinx it. Yeah, this part we can actually remove. Yeah, this is wrong now, I think. This is wrong. So actually this should be the denominator. It's just radius minus the distance of the... Yes, is this one here. So it's like the start position. Oh yeah, we forgot about the start position. Oh my god. This is the error. Oh my god. So this should be the start position, subtract some point along the wall. It doesn't need to be mid, it could be any point along the wall. And then dot product against the normal. Yeah. Yeah, yeah. We didn't actually follow the maths correctly. So there we go, that's that. And we take r minus that. And we divide by this, which we already should have correctly there. It's just velocity dot normal, yeah? And let's see. I'm gonna do this, because that feels better. And we'll see. If it crashes, it's not gonna be great. Oh my god, what? It kind of works, but also it kind of doesn't work. Okay, you know what? I'm gonna... It looks weird. Maybe we'll need a crosshair. Do we need a crosshair? Let's just draw a crosshair. Is there a crosshair here? No. So it's basically just... Can you get the screen? Wait, but we draw the crosshair. We need to draw it in like 2D mode. Can you enter 2D mode in like? When you're in 3D? Ah, we need it. Wait. No, or we just say end 3D here. And we don't have this defer. Yeah. It's just that if you have some weird continue or something in the, it messes things up, but that should be fine. Alright, so we don't need to enter mode 2D because we should already be kind of in 2D mode right now. So it's just that we don't have a camera. So now we draw a line. Well, where's the... Do we have like screen width? Why are okay. Draw a line. Wait, we could have used this one, I guess. Start. Width over 2 minus crosshair width. Let's do like, I don't know, 50? Is that too much? Actually, it's gonna be double, so let's do 25. 3D only applies to 3D drawing, draw cube. Okay. End position is gonna be width over 2 plus crosser width. Wait, this is not correct. It's just height over 2. let's do like white maybe. No. All right. Oh. God damn it. There you go. Take a circle. Oh. I'm used to the old CS, the old Counter-Strike crosshair that like it had a cross and then it expanded. Okay, this does not look great though. Let's do that. Man, then we need to do like 2 of these. Let's do void minus. Wait, that's the start, and then this minus. No, then it's gonna be like. This minus void. Oops, that doesn't work. And this, and then we do plus void. There we go. So this would be. A little bit shorter. This is very important. All right. It's like it's a little bit. It's not centered properly. I think this needs to be odd. Wait, it looks weird. Okay, does this need to be even? There we go. But now we can increase this a little bit. There we go. We have a little crosshair. Okay. And you can see, well, you can see that if we're aiming down, the raycast actually returns like, you know, it doesn't matter where you aim up and down. It just left and right. But if we aim like this, yeah. I mean, you can see that the green aligns with the crosshair, which is good, because that is like the circle. That is actually the, so green aligns with the circle, while the red. Okay, this doesn't look good. The red point is going to be the intersection point, But it seems like there's something going on over here which does not work that well. Oh, yeah, and then if the player moves into the wall, we crash because there's some weird issues here. Okay. You always disable the dynamic crosshair. It was annoying when moving. Smaller crosshair is possible for optimal headshots. Yeah, okay, I see. I kind of liked it because it showed also like how much spread you had with a weapon, I think. And if you had like a bad computer, it took longer for the spread to go down, which is strange. Yeah, we could probably find a whole bunch of issues with this now, but this basic case seems to work pretty well. And you can see like it intersects at probably the correct point. I mean, this should be the closest here. Also, if I do this, I actually stop here. So this wall seems to... I spoke too soon. Okay. We're doing... making progress. Yeah. So it was essentially pay to win. Because the better computer you had, the more you could spray and pray. With more accuracy. And my favorite weapon was the... What was your favorite weapon? Mine was the AK-47. I love to be like a terrorist and just rush every time. I hated those goddamn snipers. It wasn't like a very fun playstyle to me. I don't know. Maybe I should have played Quake instead. Quake 3 was also very cool at the time. Higher FPS essential for strafe jumping. Oh. The Colt, as we said the Colt. And Desert Eagle, yes, that was also my favorite gun. My favorite handgun. But I also liked the one you start with as a counter-terrorist. I forgot what it was called now. But the Glock is just the worst. But it's fun if you get some headshots with it. But I think the if you hit someone and they have a helm, then the Glock is like, yeah, USP, right? Yeah. The Glock is like useless. But if they don't have an helm, then hitting in the head is really nice. Because they get like disoriented and stuff. And also getting headshots with the USP was so satisfying. It was just something really satisfying when you saw those sparks coming off the head. And you hit multiple times. Yeah. Man. FAMAS? Yeah, that was... Hey, that's the new one, right? That's the new gun. It's so weird when they change stuff, because it was like you were so used to the everything, the whole meta and everything, and then they changed things around. It was super weird. But yeah. Because then you had to learn the new things. I mean, also it's kind of weird because some guns were basically never used. I think like the super expensive sniper thing that basically you could shoot. I don't remember what it's called. Or the thing what we call like the heavy machine gun, the para we called it. I guess it's used sometimes. Like if you're way ahead. And you just throw away some money at a super gun, but it could be used against you as well if you lose it. So, but the balance of those guns, I think, was kind of weird because they were basically never used in like real games, I guess. Shield, oh my god, yeah. Man, I forgot about the shield. Oh yeah, this thing. You know what? Instead of making a cube, I'm gonna do... It should be like 111. Draw circle 3D. They were too expensive for inaccuracy, although all the sniper is more precise compared to CTs. Oh really? Oh man, I didn't even realize they were different actually. It's been so long since I played. Weird balance also between terrorists and counter-terrorists was the Glock was terrible all around. Yeah. AK-47 imprecise, but it also has more damage. Yeah, but I liked AK-47 because it if you were good at aiming, you could like one shot. I believe you could one shot with the helm, right? Or if you just hit the body a couple of times, you could kill pretty quickly as well. You usually do like a 2-shot burst or something like that. Or maybe it was just a dot, wait for the precision to get down. Yeah, man. Okay, rotation axis. Also, I never knew if silencing the Colt actually made it do less damage. It feels like it should be, but so what is it? Rotation axis. Is this like... Well, I guess we'll just try something here. Hello, Gaming Hunter. What's up? What's up? Dot plus spray. Dot plus spray. Yeah, Because once you dot, they are notified of your presence. Maybe sometimes you do that. I don't remember, man. It's been so long. And then you start to panic once you miss everything. Okay, what will this do here? Rotation axis. Let's just do something here. What are we doing? We are using BSP to we're implementing a collision algorithm using BSPs and circles. We had we had like some kind of home page. I forgot what it was called now, where you could join and it was like a ladder. You could join like games. You could like registered on the site and you got like points and stuff. And you played games to gain points and stuff and reputation and I don't know what. Probably like tournaments and stuff as well. I wasn't on there too much, but it was a different time. Yeah. But we basically just played. I played with my friends. We had a clan. And we renamed our clan every month or something like that. And we went to some LAN parties like DreamHack. But yeah, we never really. But it was fun. ESEA or Faceit. Yeah, I think the one that I saw was like it had like multiple nationalities. I don't remember now. Faceit. I don't recognize the name, but that might have been it. I don't remember. I'm sure I will remember if I see the name of it, but it will probably maybe just in the Nordics or something like that. I do remember seeing like flags. It was like a red background. A red background, small text, a bunch of lists and so the rotation is along Y maybe, and then the angle is, I don't know if this is you never know if this is like, okay, I'm just gonna say 360. That should cover it. Color is green. Okay. Yeah. Okay, that was wrong. So it should. Okay, so according to this, it goes like around. So it should be like this. Wait, what? That's the same thing. What the hell? Rotation axis. That doesn't seem to do anything. Is it a bug in Raylive? Okay. Playing in SLAP. I don't recognize that. Which a Danish esport tournament and event coordinator. Okay. Man, I mean I remember when HLTV came. I think it was called. I don't remember when it was, but yeah. If you know what that is. And the first version that I started playing was the beta 5.2. I distinctly remember. But by then we didn't really go to any LANs or anything. We only went to we played like locally at a friend's house. And then we also played a little bit another game which was came at the same time, but it didn't gain nearly as much popularity, which is called Strike Force, which was a mod, like a similar mod, but it was for Unreal Tournament instead of Half-Life. But that was before, so that probably 1.3. I mean, yeah, I remember because before 1.3 or something, you could actually jump with the AWP, whatever it's called, and hit perfectly straight. So and you could jump, and usually when you stormed with pistols, you would just storm and then jump all the time, because your accuracy was 100% even when you jumped. So you would jump around a corner and just surprise the enemy, and you could shoot them at the same time. Urban Terror Quake 3 mod. Oh, I never heard of that. I never knew there were Quake 3 mods, actually, to be honest. That's cool. But yeah, we played I played Quake 3 and Unreal Tournament as well. Man, those were the days. Urban Terror was like CS on speed. Okay. With wall jumping. Oh. Yeah, okay. Interesting. Okay, so this doesn't actually work. Unless I'm using it incorrectly. I don't know. Maybe the rotation angle is weird. No. Same thing. What if you say half? Will it only show it like half, or is it doesn't do anything at all? Is this even compiling? What's happening here? It is? Okay. What if this is 0? Does that change anything? No. Okay. So this is apparently not really implemented here. Or I'm using it wrong. Draw circle, gradient. Circle. You can't play CS 1.6 without issues on your Mac. Oh. That's too bad. I mean, did you ever get into the new ones? I think I tried... Which one is the newest one? Like, is it CS2? I tried... But it's just, it's not the same, man. I don't know, it kind of has the same feel a little bit. Okay, let's draw like a, can you draw like a ellipsoid or something? Or a spheroid, whatever it's called. Draw sphere. Yeah, okay, let's draw sphere wires. Radius 1. Rings. I don't know, let's do like 5. Whoa. Now we're talking like early vector graphics. Okay. Yeah. That looks cool. Maybe we'll increase this a little bit. Rings. So what is rings? Rings and slices. CS2 is the new, okay. CS sources were not the same, yeah. Yeah, CS source was like, I just skipped that one. Oh. Hello. What the hell? I'm just exploring a little bit. Oh, it's almost, it's okay. Wow. Oh, I see. It's like the rings that go around. Okay, let's just do something like this. Okay, anyway, you can kind of see here that it's like the ball is like touching, you know, down there, the red dot is up there, but it's essentially just showing, like the y-axis doesn't matter, it's just showing where on the wall it actually hit. It's like if I'm standing over here and throw a ball this size, it will hit along the wall at some point. And here we can see that the intersection point is kind of weird because it like shows over there. I think it has something to do with how we calculate where to split and which wall segment we actually want to split on. But this doesn't make sense because there's nothing, there's no segment that goes here. It looks like the ball is correctly placed, but the intersection point is wrong. And in fact, we should, the ball is as large as the player right now. So if we move against the wall, we should stop at the same kind of distance that the ball has against the wall. But that doesn't seem to happen. I mean, you can kind of see it kind of works, but we can very easily go through the wall. I'm not sure what the issue is, but it might be Normal's lookoff. The thing is that Raycast works flawlessly. So it's something, I think the BSP tree is correctly done. It is, I think it has to be something in this algorithm that is not up to par. The worst thing was with CS Source. It was a bug where physics were really flippant. I would drop a nade and the barrel would fling and kill me. Oh. Right. Yeah. I think what they wanted. I think they tried really hard to replicate the original physics and stuff with the new one, because it does feel very similar. And especially like, you know, you have the gun play. It was just so. I mean, yeah, the original was just something so satisfying, getting like headshots and that. And it's also like if I think back about it now, it's kind of with rose tinted glasses, you know, the graphics looks probably, you know, it probably looks better in my head than it actually looks. But the thing is with CS, I don't really care about the graphics. It's more the gameplay. Does it only happen when the ray intersects through a split plane? So here you can see the normal kind of the normal raycast works. This thing, yeah, I mean it does seem to work pretty well. Also, when you go off like this, actually, can you see here? As long as we, oh, I see. If we do like the crosshair goes outside, you can see here here's the line of the wall. Oh, I was gonna say like as long as we're inside the wall it works, but that was apparently not true. It's like when we're at the corner. Maybe that's the issue. Like we're in a corner, so we're technically kind of colliding maybe over here as well. We have like multiple splits, but I don't know where this intersection point is coming from, because there's no segment over here. There's no segment that cuts through here, so I'm not sure how this intersection point is calculated. Maybe something is wrong with the calculation of the intersection point. So how I'm doing this is basically I keep track of the last kind of the last node that was causing a split, which works really well for the raycast to understand what segment we're moving along. But for the circle intersection, we might have like multiple. Yeah, we might have multiple actually this might be how. So it looks good now here. It even looks good here. But as long as we're at the corner, actually this corner looks fine. Although that looks weird. That doesn't look right. Okay. What the hell? It's like something like invisible extending over there. I mean, it kind of works. It's a rather large object we're shooting here as well, so maybe if we change the down a little bit, we'll get some more interesting things. Let's do like 0.3. Wait. So imagine now we're shooting like a, oh, interesting. There's a small section here where it goes through. But it goes, you can see it goes through kind of weirdly. It goes, it's like it's ignoring this and getting stuck on this one. Okay. So I think it's because we're doing one sweep in Quake, according to AI. It's like if you're in like a wedge, let's say, and you have multiple walls that you might collide with, it's actually adjusting you for one of the walls first, and then it runs the collision algorithm again. So it adjusts your position and your velocity to run along the wall, and then it runs the collision algorithm again, and if you collide with the other wall at that point, you're adjusted again. But then if you're in a wedge or in like a crevice that's very an acute angle, there's like a special fix for that. So, but yeah, so yeah, ship it. Yeah. Look at this. I wonder why we're facing into the wall. Like if I move like this, it's kind of getting stuck in this like event horizon over here. Let's do, I think this is the issue as well. I think we don't look at the intersection point. We want to look at the I mean, essentially it's just going to be the velocity, right? We take the velocity, so that gives us the direction. Wait, there we go, we don't need this. So we take the velocity direction, so we basically essentially move back. A little bit to avoid facing through the wall. That's the idea. Isn't BSP also meant to draw parts of the map? Yeah. Oh. It crashed. What if we increase this here a little bit? It's like we're adjusting a little bit to move back from the wall. It apparently does not work too well. We can always sneak past. And also it's like it doesn't matter. You can see we're kind of getting stuck here, but we always get through. So do something like this. Yeah, I can show you here. So one thing that we did to optimize the rendering that I can show you here. I just need to modify the speed of when we go up and down, because it's modified to be the acceleration. So I think if we do this, we might get the correct perhaps thing. Yeah. So here you can see still kind of quick. You can see the back, the walls that are like away from us, like they are facing away from us. Those are not drawn at all. So we're skipping drawing a bunch of walls, depending on if they're facing us or facing away from us. So this, and that's thanks to the BSP. The BSP tells us which walls are facing us, which walls are facing away. Yeah, it's also, yeah, that is also true. Like it is also like a GPU thing as well. But we never send the draw call for those walls to the GPU. But the GPU will also hide those walls for us depending on how you draw it. So I don't know if we actually optimized anything, but yeah. I mean, we're saving a call, so I think what we need to do, we just need to meticulously go through this code over and over again until we find the thing that is wrong. We could do a bunch of logs to figure stuff out. We could disable the... I mean, what's kind of weird is that this seems to work, but when I move towards it, it's so easy to get through. Why is that? It like calculates that we are intersecting every time, but when we are right up against the wall, even with like bounce back that we have here, the over bounce, it bounces back. We go back a little bit. Another thing you could do is no. This doesn't, I mean, it doesn't feel like this is doing anything though. We're changing the velocity here. This just goes back the original velocity. So that should just move us back a little bit. It's like away. If we're essentially, we want to move away from the wall, which is essentially, it's the normal of, I guess it's the normal of the wall instead. Maybe we want to use. So we could make this be the normal of the wall, which should be normalized. And move in that direction a little bit. Or will that make us like move along in a weird way? Maybe, I don't know. Oh, god damn it! Too fast. Yeah, maybe. So let's do like vector 3. No, it doesn't seem to be any different. Actually, it seems a little bit worse. I mean, it doesn't even seem to do anything. It's only when you actually collide, though, so that we have to keep that in mind. Wait, but now we're moving away. Yeah, the normal is away from the wall, so we should add, not subtract. What? Okay, I was hopeful there for a little bit. Let's. I guess we can increase it a little bit. It seems like a lot, though. Now it's like we should bounce. Yeah, look at this. Even with this, we can move through. I mean, that might just be a flaw in the actual collision detection, though. Like when we're close to the corner there. No. If we just move forward, we go through. That's so strange. Like, yeah, that doesn't, I mean, yeah. It seems kind of random as well. Welcome back, Penguin. So it's like if I increase this to like even more. Okay, this might actually be because we're perfectly perpendicular to the wall. We're moving in a perfectly perpendicular. If we do this. Okay. Hang on, I need to test if. Oh my god, what the hell? Yeah, sometimes it just doesn't register an intersection, I think. What if we did this? If we get an intersection here, we record that. So I'll just log this out. And it's always gonna, this is always gonna be a branch, and we should have an ID. So if I just move forward now, You can see it collided. And there was no collision. It's like totally random, almost. It's like it's charging up energy. What the hell? Yeah, I think we'll have to leave this one now. I don't think we'll get much further right now. But yeah, I mean, I think we made a lot of progress though with this algorithm. We just need to figure out a few kinks here and there. I might watch that video, Minkowski Sam dialog, and yeah, I'll probably watch it off stream though to get this moving a little bit. Maybe I'll watch it like tonight or something. But yeah, that's gonna be it for this time. Thank you very much for joining and chatting with me. And I wish you a good day.